Hi, everyone. Welcome to session 4 of the Great Lakes Coastal Wetlands webinar series hosted by Environment and Climate Change Canada and Toronto and Region Conservation Authority. My name is Sharon Lam, and it is my pleasure to moderate today's webinar session. I'm a project manager with the Ecosystem and Climate Science team at Toronto and Region Conservation Authority, and I'm joined by an amazing group of colleagues in both ECCC and TRCA, some of whom you'll meet over the course of this afternoon. Let me begin by taking a moment to respectfully acknowledge that all of us at this virtual meeting, no matter where we are located on land that has been home to Indigenous nations since time immemorial. We respectfully acknowledge that the lands we are situated on are traditional territories and treaty lands, in particular, those of the Mississaugas of the Credit, the Anishinaabeg of the Williams Treaty First Nations, the Huron-Wendat, the Haudenosaunee, and are now home to many diverse First Nations, Inuit, and Métis peoples. We appreciate and respect the history and diversity of the land and are grateful to have the opportunity to work and meet in this territory. And we are honored to be joined by representatives of Indigenous organizations at today's webinar and at our previous sessions as well. Let's now go over some quick housekeeping notes. Today's session is being recorded, and a copy of the recording and slides will be shared with all of you in a couple of weeks following the completion of the webinar series. All participants are muted and video disabled to minimize disruption and save bandwidth and emissions. Please use the Q&A box at the bottom of your Zoom control panel to post questions throughout today's session. You can also upvote others' questions in the Q&A. To share comments, please use the chat, and thank you to all of you for sharing with us in the chat your name and where you're calling from today. It's great to see some familiar names. Closed captioning is available in English, and you can enable or disable this by clicking the CC icon at the bottom of your Zoom control panel. If you encounter any technical issues with Zoom, please send an email to Jessica for support. And with that, let's now take a look at what we have already covered and what we still have planned for you before the end of this week-long 5-part webinar series. The first 2 webinars on Monday and Tuesday focused on the results of Environment and Climate Change Canada's Great Lakes Coastal Wetlands Climate Change Vulnerability Assessment. Session 1 focused on the results of the climate, lake level, and wetland response modeling developed by Environment and Climate Change Canada. And Session 2 focused on the remaining results from the vulnerability assessment, including wetland sensitivity, adaptive capacity, and overall vulnerability. Over the course of sessions 3 to 5, yesterday, today, and Friday, we will explore different climate change adaptation strategies and options to enhance the resilience of Great Lakes coastal wetlands, with guest speakers from across the Great Lakes Basin. Today's session will focus on coping with lake level extremes, managing diked wetlands, and restoring biodiversity, including invasive species management. If you missed previous sessions, we do hope that you'll check out the recordings once they are available in a couple of weeks. Jessica has shared a link to the detailed agenda in the chat, and hopefully you'll be able to join us for our final session tomorrow as well. Through these webinars, we hope to engage coastal wetland practitioners, describe Environment and Climate Change Canada's vulnerability assessment, modeling, and analysis, which we've done over sessions 1 and 2, share the results of the climate and water level projections, wetland sensitivity, adaptive capacity, and vulnerability, and explore best adaptation strategies and options to enhance coastal wetland resilience, which we are looking at through yesterday, today, and tomorrow. With that, let's take a closer look at what we have in store for you today. We will begin with a presentation by Greg Main and Anders Holder, who will provide an overview of Environment and Climate Change Canada's white paper on solutions to enhance Great Lakes coastal wetland resilience, which was prepared as part of the Assessing and Enhancing the Resilience of Great Lakes Coastal Wetlands project. Greg and Anders' presentation will help set the stage for our 6 guest presentations today, starting with a joint presentation by Mike Schatz and Joe Fiorino from ECCC on the adaptive management approach to supporting Great Lakes St. Lawrence River outflow management. We will also hear from Dr. Adam Beckley from Wisconsin Sea Grant on nature-based shoreline options for Great Lakes coasts. On managing diked coastal wetlands, we'll hear from Heather Pankhurst from Central Lake Ontario Conservation Authority. We will then take a quick 5-minute break and come back for part 2 with 3 presentations focused on invasive species management, including another joint presentation by Marianne and Dominic, whom you may recall from session 1, on their modeling of the impacts of climate change on the growth of cattails and Phragmites. Heather Braun from ECCC will share with us lessons learned from the large-scale management of invasive Phragmites in the Long Point region of Ontario. And finally, we will also hear from Karen Alexander from the Invasive Species Centre on novel approaches for collaborative Phragmites management and financing. We'll be taking a few questions after each of the presentations as time allows, and we'll also have a collective panel discussion at the end. So please input your questions in the Q&A throughout the presentations, and where possible, please address your questions to specific speakers. I will now invite Greg to please share his screen while I provide a brief introduction to Greg. Greg Main is the Habitat and Species Unit Head with Environment and Climate Change Canada's Great Lakes Ecosystem Management Section. Greg began his career as a biologist with the province and later as wildlife toxicologist with Canadian Wildlife Service. Since 2004, Greg has co-developed various Great Lakes plans, including lake-wide action and management plans, biodiversity conservation strategies, baseline coastal habitat surveys, initiatives for community-based action, and most recently on coastal wetland vulnerability, resilience, and adaptation. And Greg, I see that your presentation is now up and in full presentation mode, so I'll pass the floor now to you.
Thanks, Sharon, for that introduction. So just a few slides today in the interest of time, given the lineup of speakers that we have for you today. Really, my goal is to provide some background as usual, and then introduce a recent guidance document on coastal wetland resilience and adaptation that was developed as a part of this study. Recalling our study goals and outcomes from previous presentations, we began the week by discussing the methods and results of our coastal wetland vulnerability assessment. And then we transitioned to resilience and adaptation yesterday with excellent case studies and adaptation options from our speakers. This in an effort to build a better understanding of climate change, plausible wetland responses, and best approaches to enhance wetland resilience through adaptation. We heard that across the Great Lakes, coastal wetlands have been responding to climate change in ways that are difficult to understand and hard to predict. We've lost a huge proportion of coastal wetlands since pre-settlement times, and our remaining wetlands continue to be threatened by conversion to other land uses and from watershed stressors. It's crucial to understand and ensure that remaining wetlands are resilient or remain resilient because of the many ecosystem services that they provide to the Great Lakes freshwater ecosystem and to the Great Lakes population, as well as our economy. And those ecosystem services are shown for you in this caption on the slide. Regardless of any mitigation measures, resilience and adaptation should be cornerstones of conservation moving ahead. Recall also that we have some rather theoretical concepts to understand. For example, our focus on resilience is best defined as a trait or a capacity of a wetland to cope with climate change. In contrast, adaptation refers to the deliberate actions that we can take to adjust to climate change or moderate or avoid harm and to enhance resilience. What makes this challenging is that resilience is a theoretical concept. It's still being explored and put into practice. I had to alter the slide after the excellent case example shared yesterday by conservation authorities on Lake Ontario and the US Army Corps of Engineers, who integrated climate and physical modeling into the design of waterfront wetland restoration projects and other wetland creation projects. And these served as excellent examples of adaptation. But suffice it to say that there can be other challenges and the benefits far outweigh the costs of putting the effort into really understanding what resilience is and coming upon adaptation strategies. In our study, enhancing coastal wetland resilience through adaptation began with assessing vulnerability and working with local partners to identify best adaptation options. Ultimately, what follows would be the design and implementation of projects, evaluating the outcomes through performance indicators, and sharing experiences and continuous learning. As I mentioned yesterday, the most important aspect of adaptation are people, the communities involved, partnerships, and institutions working and learning together. Given the many wetland values and climate change risks, Environment and Climate Change Canada undertook a coastal wetland vulnerability assessment. Recall that this study integrated physical variables as well as biological information to understand how wetlands could plausibly respond to climate-driven water levels. The modeled outputs were then used to inform a wetland sensitivity analysis to determine potential impact. And this was then combined with an analysis of adaptive capacity as shown on this slide. If you missed these presentations, the TRCA has recorded them and they'll be made available to you. Here again is a graphic that illustrates the wetland class distribution studied. And note that they occur from the driest on the left to the wettest on the right as vegetation transitions along a hydrological gradient. So that was very much the emphasis of our study, wetland vegetation rather than wetland wildlife. The results of our study can be found in several technical papers, but for today, I simply want to show this map again that integrates information and shows the vulnerability for each of our 20 coastal wetland study sites. What you see is the intermediate greenhouse gas emission scenario, RCP 4.5, and specifically the results of the lower bound scenario with future lower or stable water levels shown on the left-hand side of each circle, and the upper bound scenario with higher water levels shown on the right-hand side of the circle. Wetland vulnerability ranges from very low on this map, which is seen in green, to very high, which you can see in dark red or crimson. High-level results, in the interest of time, is that we found that wetland vulnerability differs across all wetlands that were studied across the Canadian Great Lakes. All wetlands in the studies are found to be at some level of risk, and that is to say, somewhat vulnerable. Vulnerability is most pronounced under the upper bound scenarios, with projections for higher lake levels shown on the right-hand side of each circle. And we can see that some of the most vulnerable wetlands are located in Eastern Lake St. Clair, the Detroit River, Western Lake Erie, and to a lesser extent, Western Lake Ontario. These results were explained in great detail over the last couple of days. And again, they'll be made available to you in papers. Given our results for climate exposure, sensitivity, adaptive capacity, and overall vulnerability, all wetlands could be enhanced for improved resilience. Building on our vulnerability assessment and discussions with many of you over the last couple of years, we developed a guidance document that introduces the concept of wetland resilience and adaptation. The paper provides details and the rationale for 6 overarching adaptation strategies with associated measures and options. It involved a comprehensive literature search and synthesis, reviews by a multi-agency advisory committee, and your input through questionnaires, interviews, workshops, and reviews. Several authors contribute to the paper, and special thanks goes to the Climate Risk Institute, the GEI Consultant Services, my staff, and our wetland working group. Also to Pete Suzuk for his input on coastal management and geomorphology, and to Linda Morsch for her attention to detail through the editing process. So adaptation is pretty complex. There's no one-size-fits-all solution. So we organized our thoughts and we borrowed from other models and constructed a framework that consists of a continuum of adaptation options, ranging from very large or overarching resilience pathways, such as resistance, resilience, and transformation, to high-level adaptation strategies, to more detailed adaptive measures, and finally, a very large suite of options with examples gleaned from the literature. There are many adaptation approaches out there. However, we landed on 6 overarching strategies with over a dozen nested measures and, as I say, a suite of potential options. In the interest of time today, I want to quickly pass this over to Anders Holder to introduce our 3rd and 4th strategies that are shown on this slide in front of you, recalling, of course, that we went over the first 2 strategies yesterday. So over to you, Anders.
Thanks, Greg. Good afternoon, everyone. Today I'll be introducing adaptations strategies 3 and 4, which will be found in the report that Greg was mentioning, Adapting to Climate Change Solutions to Enhance Great Lakes Coastal Wetland Resilience. In the interest of time, I will briefly touch upon both strategies and a couple measures that will complement the presenters. Strategy 3 addresses the need to maintain and/or restore biodiversity and functional redundancy of coastal wetlands. Biodiversity refers to the variety of all life within coastal wetlands, including diversity within species, between species, and among communities in which species live. Functional redundancy refers to the replication of multiple ecosystem components or taxonomic groups that share similar roles in ecosystem function. Together, biodiversity and functional redundancy promote coastal wetland resilience and stability. The key adaptive measures within this strategy are enhancing community structure and native species populations, controlling invasive plant species, and conserving and restoring native plant species and communities. So why is this strategy important? We recognize that greater species richness leads to an increase in overall ecosystem function. The degree to which the loss of an individual species impacts overall structure and function depends on whether there are other species within the community that perform a similar ecosystem function. Most ecosystem services are produced by multiple components, and diversity allows for some of these components to persist through a disturbance and continue to deliver on a particular ecosystem service. Redundancy provides insurance for wetland ecosystem services by allowing some components to compensate for the loss of others. The maintenance and restoration of biodiversity and functional redundancy can enhance the resilience of wetland ecosystem services by providing options for responding to change. When coastal wetlands can no longer support diverse populations and communities of native wildlife, or when existing anthropogenic stressors are compounded by climate change, active restoration may be required. This measure presents options for enhancing community structure and native species populations. Examples of adaptation options include restoring interspersion by managing non-native cattail and Phragmites in the lower Great Lakes wetlands, increasing microtopography in created and restored wetlands, and creating vernal pools or palustrum wetlands where they have been isolated, degraded, or lost. After habitat loss, non-native invasive species are considered the most significant threat to biodiversity. Non-native invasive species can alter habitats and essential ecosystem functions, including hydrology, nutrient cycling, and energy flows. This measure presents options for controlling invasive plant species. The map on the right shows a summary of Phragmites abundance in Long Point, taken from the results of the Canadian Great Lakes Baseline Coastal Habitat Survey. On the map, in terms of aerial extent, it's shown that approximately 18% of all wetlands within Long Point have been replaced by Phragmites. The actions targeting Phragmites and non-native cattails are the focus of this measure. Examples of adaptation options include creating regional and coordinated invasive plant management strategies, and developing an integrated pest management program that's proactive and preventative, which incorporates a combination of treatment options and is species and place-based. Additionally, within this measure, several adaptation options have been developed specifically for Phragmites as well as non-native cattails. Recognizing that there may be future extreme lake levels, including lower lows and higher highs, Strategy 4 focuses on accommodating possible hydrologic shifts, including sustained, rapid, alternating, and extreme lake level changes. The key adaptive measures are managing wetlands to cope with sustained periods of high lake levels, managing wetlands to cope with sustained periods of low lake levels, managing and enhancing the resiliency of diked wetlands, and removing, realigning, and relocating wetland constraining infrastructure. So why is this strategy important? The variability of lake levels from both natural processes and water level regulation can present challenges when planning for changes in the Great Lakes water levels. However, it is the modeling projections for the higher highs and lower lows that are of most concern. There are detrimental impacts associated with frequent, extreme, or sustained periods of lake level change. In 2019 and in 2020, each of the 5 Great Lakes were at or near all-time record high water levels in the recorded history. As water levels rise above these historic heights, wetland area and aquatic habitat could decrease because of inundation or become lost if shoreline structures, land use, or topography impede the landward migration of wetland vegetation. Conversely, under an extreme or prolonged low lake level scenario, wetlands can dry up, becoming disconnected from the lake or decrease in size, and this transition to drier meadow or shrub plant communities. Shoreline erosion in southern Lake Huron and much of Lakes Erie and Ontario is underway. And while this is a natural process, the erosion is being exacerbated by shoreline development and hardening. Additionally, high lake levels and changes to wave climate, mostly due to the warming water temperatures, will reduce the duration and extent of ice cover and increase shoreline exposure to storm events. There is a need and opportunity for innovation, particularly related to the design and implementation of approaches where natural and built infrastructure are combined to provide maximum coastal protection benefits while still providing the social and ecological services. This measure presents options that will help enhance wetland resilience under extreme high and/or prolonged high-level lake level regimes. Examples of adaptation options include planting native wetland plants that are adapted to the high lake levels while undertaking wetland restoration, and controlling undesirable species that respond to these higher lake levels, like non-native cattails and Phragmites, and additionally restoring protective barrier beaches or beach ridges and sand spits that historically protected coastal wetlands. And in addition to the high lake levels, periods of extreme or sustained low lake levels are also expected to occur. And while periodic water level drawdowns can have benefits on wetland biodiversity, drawdowns may also benefit invasive species. Prolonged low lake levels can result in wetland stranding if they get cut off from the lake, or meadow vegetation can dominate at the expense of aquatic habitat. This measure presents options to help cope with the period of low lake levels. Examples of adaptation options include protecting and managing the original wetland area and the riparian buffer from development or alteration during these periods of prolonged low water levels, interseeding with plant species tolerant to low lake levels, and specifically in sites with open wetlands that are dry, and controlling invasive species that favor these low lake levels, such as non-native cattails, that may expand or become more dominant behind the barrier beach ridges. Thank you for your time, and I'll now pass it back to Sharon.
Wonderful. Thank you so much for the great overview, Greg and Anders, and for setting the stage for our 6 guest presentations today. We will save questions for Greg for the panel discussion at the end, so please do keep inputting your questions in the Q&A. We'll now hear from our first guest speakers, Mike and Joe. Mike, please go ahead and share your screen while I provide a brief introduction. Mike works in the Boundary Waters Issues Unit of the National Hydrological Service within Environment and Climate Change Canada. He currently serves as the Canadian Co-Secretary of the International Joint Commission's Great Lakes St. Lawrence River Adaptive Management Committee. Joe Fiorino is a habitat ecologist with the Canadian Wildlife Service within Environment and Climate Change Canada. He is the CWS lead for multiple Great Lakes coastal wetland monitoring programs. And Mike, I see that you're all good to go. The floor is yours.
Good afternoon, everyone, and thanks for the opportunity to present on some of the work of the Great Lakes St. Lawrence River Adaptive Management Committee. As Sharon introduced, my name is Mike Shantz. I'll start by presenting some context on Lake Ontario outflow management and Plan 2014, as well as the adaptive management framework, and then I'll pass it over to Joe Fiorino to get into the details on wetland monitoring and assessing response to water level changes in support of our adaptive management efforts. So in this presentation is focused on work related to the management of Lake Ontario outflows into the St. Lawrence River. And outflows are managed at the Moses Saunders Dam at Cornwall, Ontario and Messina, New York, which was put into operation in the late 1950s. And at the time the dam was constructed, significant changes were made to the St. Lawrence River that affected how much water can be conveyed through the system. And so collectively, these modifications have led to changes in Lake Ontario water levels from what would have occurred naturally. So Plan 2014, which I referred to earlier, is the name of the outflow management plan that currently governs flows leaving Lake Ontario and going down through the St. Lawrence River. The International Lake Ontario St. Lawrence River Board, or BORD, as I'll refer to them in this presentation, is responsible for specifying the outflows from Lake Ontario in accordance with Plan 2014. So flows from Lake Ontario travel down through the St. Lawrence River, past Montreal and to Lac St. Pierre and beyond. Outflows from Lake Ontario are managed in consideration of levels and flows both upstream and downstream of the structures. So water levels of Lake Ontario and the St. Lawrence River fluctuate naturally, and it's important to note that the ability to alter lake levels through regulation plans is limited and is dominated by changes in water supply, particularly during wet and dry periods. So if conditions are very wet, you're likely to see higher water levels on Lake Ontario and throughout the system in response. And if conditions are very dry, you'll see lower levels. And while Lake Ontario outflow regulation can have an influence on some of the more extreme water levels, it will certainly not eliminate extreme levels in the future. So the question from our adaptive management perspective is, so what are the benefits and impacts from the current outflow, water outflow management strategy for Lake Ontario? And has the adoption of Plan 2014 improved outcomes in the system relative to how things were managed previously? And could things continue to be improved if even more in the future if the current outflow management strategy were to be modified at all? So the Great Lakes St. Lawrence River Adaptive Management Committee, or the GLAM Committee, was established by the International Joint Commission in 2015 as a subcommittee of the 3 Great Lakes boards. And the GLAM Committee assists the IJC's boards in systematically reviewing the water outflow management plans in the system, which includes Plan 2012 for the outflows from Lake Superior and Plan 2014 for the outflows from Lake Ontario. The GLAM Committee is not a decision-making body, but rather we work to gather information and build tools to help support the boards in the IJC when reviewing their regulation plans. This image shows the adaptive management cycle. The point behind adaptive management is that we take an applied learning approach that recognizes that no matter how much we know, there's always more to learn, and that a system as large and as dynamic as the Great Lakes St. Lawrence River system is always changing and sometimes in ways we can't even imagine, let alone predict. So with adaptive management, decisions are made based on the best evidence to take action, and then we monitor the key outcomes from that decision and challenge the decision if the outcomes aren't as expected, and make the necessary adjustments, whether that is to how the board deviates under future extreme water level conditions, or maybe it's improvements to the regulation plan itself as more is learned and as conditions change. So this is the purpose of our review of the regulation plans. In our adaptive management process, we're looking closely at ways to understand how outcomes might change under different water level conditions, as may be influenced by our outflow management or outflow regulation strategies. And these graphics are meant to help illustrate what those differences might look like, but they can be a little difficult to interpret. So I'll highlight a couple aspects here. The graph has 101 years of simulated Lake Ontario water levels on it. So each line represents a year of water levels from January through to December. So the graph on the left illustrates essentially non-regulated conditions, or essentially what water levels that would have occurred had the dam and modifications in the upper St. Lawrence River channel not taken place. You'll see that there is seasonality to water levels, obviously, typically peaking in the early summer and declining in the fall. You also see that's a fair wide range on this graph, with some years that have very high levels continuing throughout much of the year, some very low, and along with a bunch that are somewhere in between. This next graph is similar, but using water levels that would be expected to occur under those same water supply conditions, but with Plan 2014, the current outflow strategy for Lake Ontario. So you'll notice right away that the seasonality is still there, but that the overall range is much reduced from what would have occurred under non-regulated conditions or when if the system had not been changed, and that there's a little less variability from year to year, certainly relative to non-regulated conditions. And finally, here's that same graphic for the regulation plan that was in place prior to Plan 2014. So again, you'll see that there are some high and low years, but water levels tend to be much less variable, particularly from non-regulated conditions. So this change from non-regulated conditions to regulated conditions, including reduced year-to-year variability in water levels, is recognized to have some influence on vegetation response in Lake Ontario coastal wetlands. So one way to assess or compare outcomes from different outflow management strategies is to simulate potential benefits and impacts under different water level conditions, along very similar to the work that was discussed earlier this week by the coastal wetland response model. So this is a fundamental aspect of our adaptive management process, where we work with experts to build tools and models to simulate potential outcomes for key indicators as driven by changes in water levels. And in the context of our discussion today, ecosystem outcomes in particular are a critical component, and more specifically, vegetation response to coastal wetlands. So as you saw in the previous slide, there have been fairly significant changes in water levels after the implementation of the dam, which has implications for wetland vegetation response. And while it's not possible to return to what conditions were like before the dam and the modifications to the St. Lawrence River, there might still be ways to improve the current outflow management strategy. So the GLAM Committee is guided by an adaptive management framework for our long-term efforts, which identifies critical components needed to make this process successful. And for today's discussion, I want to particularly draw your attention to this middle box, if I can highlight there, in terms of developing and using predictive models to assess potential alternatives from different outflow regulation plans, along with this feedback loop that emphasizes the need for ongoing monitoring to key indicators as part of the adaptive management process to ensure that what we're seeing in the real world reflects what we expected based on our simulations. And that monitoring is also critical as it informs improvements to our scientific understanding and our ability to improve models in the future. And this is where the wetland monitoring efforts that Canadian Wildlife Service has been doing are so critical to our work. And so I'd like to turn it over to Joe to discuss that aspect in more detail.
Thanks, Mike. So hello, everyone. My name is Joe Fiorino, and I'm a habitat ecologist with the Canadian Wildlife Service. Today, I'm going to talk about some of the work, the wetland monitoring work that our group has been involved with over the last decade. So coastal wetlands are dynamic and complex environments that are critical components of the Laurentian Great Lakes. These systems provide essential habitat for birds, mammals, reptiles, amphibians, fish, invertebrates, and beyond that, provide ecosystem services such as nutrient and sediment retention, which ultimately improves water quality and protection against shoreline erosion. These systems also have immense recreational and cultural significance. That all said, there are hundreds of coastal wetlands on Lake Ontario that are affected by outflow regulation. So just to put your attention to the figure on the left, which shows water levels on Lake Ontario over the last century. You can clearly see just how different water level fluctuations have been pre versus post regulation. In terms of coastal wetlands, one of the notable consequences of regulation has been the expansion of cattails, primarily at the expense of meadow marsh, which we also sometimes call wet meadow. But of course, it's really not that simple, as wetlands are extremely dynamic. So the Canadian Wildlife Service and our group specifically has developed an approach to track changes in vegetation in response to water levels over time. But before I get into that methodology, we've seen this figure a number of times this week, but I'm going to spend a little bit more time explaining this phenomenon known as vegetation zonation. So in coastal wetlands, wetland plants grow according to their water tolerance. So this means that certain plants will grow exclusively in wetter areas, plants like lilies, while others will grow in drier areas like shrubs. So this results in groups of species growing in fairly distinct zones along an elevation gradient, which you can see depicted in this figure. So from open water to upland, wetland vegetation zonation typically occurs with submerged aquatic vegetation occupying the niche below the surface of the water, emergent vegetation occupying the shallow water or wet substrate, meadow vegetation directly above the shoreline, followed by shrubs, and finally trade areas. And this probably isn't surprising, but water level fluctuations are expected to influence these plant communities. For example, high water periods will stave off encroaching shrub and upland species, and low periods will allow meadow marsh species to regenerate from buried seeds and limit the expansion of dominant emergent species like cattails. Okay, so just getting back to our work. So our team goes out and we survey wetland vegetation at 20 centimeter elevation intervals, starting at 74.0 meters and ending at 76.0 meters. And that's based on the International Great Lakes Datum, but you can think of that as the height above sea level. So those sampling locations are shown by the arrows in the left figure, which we locate using a high precision, real-time kinematic differential GPS system, which is shown in the picture on the bottom right. And this elevation range corresponds to roughly 80 centimeters below the shoreline to 1.2 meters above the shoreline relative to the long-term average for Lake Ontario. And we do this along 6 to 12 transects, which you can see depicted in the top right figure there, for about 16 wetlands that we sample annually. And here are some examples of what those sampling locations actually look like. So the photo on the top right shows me nearly flooding my waders at the lowest or deepest water elevation, 74.0. To the left of that is a slightly higher or shallower water elevation, which is dominated by non-persistent emergent vegetation. And then the photo below that shows a higher elevation just above the shoreline. And as we all know, and we've talked about a bunch this week, in 2017 and 2019, there were record high water levels on Lake Ontario. And this past year, we had very low water levels relative to the long-term average. So peak water levels actually differed by about a meter in 2019 compared to 2021, which is pretty mind-blowing when you think about 1 meter of water multiplied by the entire surface area of Lake Ontario. It's a lot of water. So this has provided a pretty unique opportunity to assess vegetation community response to extreme water level fluctuations. And specifically through monitoring, we can track vegetation changes over time, which ultimately improves our understanding of how wetlands respond to fluctuating water levels on different timescales, and also supports validation and calibration of predictive models that inform adaptive management for outflow regulation. And as I'm looking at these photos, I'm realizing that I might be unintentionally implying that these are the same wetland, which is not the case. These are 2 different sites. They just represent extreme examples of how things differed in 2019 compared to 2021. And yeah, now I'll briefly go over some results. So this first slide shows average cattail coverage at each sample elevation for all of our study sites over time. So these figures can be a bit challenging to interpret, so I'm going to spend a minute breaking them down. So firstly, you can see that there are 6 panels, the first representing an average of all of our sampling years prior to the 2017 high water year, followed by each subsequent year. And then within each panel, there are 11 boxes that summarize vegetation coverage at each sample elevation, with cover on the y-axis and the elevations on the x-axis. And then the lowest elevation is on the left of each panel, and the highest elevation is on the right of each panel. So that corresponds with the diagram shown at the bottom. And then for each box within each panel, the center line represents the median or the central tendency of the data, and the size of the box and the whiskers represents the amount of variation in the data. Okay, so the first thing I want to highlight is that high waters seem to result in an upland shift in peak cattail coverage. So before 2017, peak coverage occurred at 74.8 meters, but it was actually 20 centimeters higher in 2019. The next thing is that there were notable changes in cattail coverage at its upland extent over time. So prior to 2017, there were little to no cattails at an elevation of 75.4 meters, just shown by the blue boxes. But there was a notable increase in 2019 that suggested that the cattails were advancing upland into the meadow marsh zone under these high water conditions. So it's also worth mentioning that there wasn't an immediate change at this elevation in response to high water in 2017. Suggesting that it was actually the cumulative effect of multiple high water years that led to that advancement. However, this may not be persisting, as we saw a decrease in coverage at that elevation last year when water levels were low. And lastly, with respect to cattails, there was greater cattail coverage overall before 2017 compared to all subsequent years. But this was especially evident this past year in 2021, suggesting that these extreme water level fluctuations have reduced the density of cattail stands. Moving on to meadow marsh. With high water in 2017 and 2019, we saw a significant reduction in meadow marsh coverage at lower elevations and a decrease in meadow marsh extent overall, which isn't terribly surprising given that most of the meadow was underwater for the majority of the growing seasons in those years. But then with low water in 2021, we saw a significant increase in meadow marsh coverage at lower elevations that resembled pre-2017 conditions. And was actually even higher than pre-2017 conditions at 74.8 meters, which is the leftmost box inside of those green rectangles. And lastly, for shrubs, These results were a little bit more straightforward. So we saw a substantial decrease in shrub cover across the entire zone following high water in 2017, and there really hasn't been all that much change since. That being said, I think taken all together, these results really demonstrate the dynamic nature of coastal wetlands. And yeah, just some key highlights. So ongoing wetland monitoring has and will continue to be critical to adaptive management. It allows for the tracking of vegetation changes over time. It refines our scientific understanding of how wetlands respond to changes in water levels on different timescales. And it supports model validation and improves our ability to predict potential future outcomes associated with outflow regulation. And yeah, it's absolutely worth mentioning that these data are also suitable to model wetland response to climate change related to changing water levels. And they were in fact used and fed into the coastal wetland response model that underpinned the vulnerability assessment presented in this series earlier in the week. And I'll just leave you with this final point, which is that adaptive management is an ongoing process. We continue to gain insight by doing work like I presented here, and then we adjust accordingly. So thanks for listening. Yeah, Mike and I can answer any questions if there are any.
Wonderful. Thank you for the excellent presentation, Mike and Joe. I'm sure there is a lot of questions from the audience, so please input your questions in the Q&A box. Our first question is to Mike. Mike, the shared vision modeling is very interesting and goes to show the different interests that need to be balanced in assessing outcomes. And as you've noted, the GLAM committee is not a decision-making body, but in evaluating plan performance, do you look at how well plans have balanced interests on the ground? This touches on Mary's question in the Q&A.
Yeah, thanks for the question. Yeah, I mean, the shared vision model that was illustrated in the slides is really meant to reflect all interests that might be affected by changing water levels or outflow regulation. So today our discussion was obviously focused on wetland response as one indicator that would be used in a modeling approach like that, but we certainly consider the intent of a tool like that is to incorporate impacts from a variety of sectors sort of within one umbrella of a decision support process.
Great. And just as a follow-up then, Mike, how often is this predictive modeling updated, and does it consider stakeholder input?
Yeah, thanks for the question. I guess taking a few steps back. So the bulk of this work, and it was initiated almost 20 years ago as part of a large scale review of the Lake Ontario regulation plan. And so a lot of thinking was done at that time and models developed. Now, since more recently with this adaptive management committee that's been established, our effort is to more frequently, I guess, update these models and tools, and we work with partners to do that. So, all this work that's been discussed this week about the coastal wetland response model is we see that as sort of the next generation of our sort of wetland model and predictive tools that we can use for adaptive management. So we're sort of constantly updating these things, but it goes in I guess, a bit in spurts depending on where we can leverage other opportunities and work with others to move these things forward.
That's great. Thanks, Mike. And I will just draw your attention to the study that Mary had shared with us in the Q&A in case of interest. My next question is to Joe. Joe, through your monitoring work and research, are there particular indicators that serve as good early warning signals for early detection of impacts to coastal wetland health?
Yeah, absolutely. So I'm gonna take that. You can take that a number of different ways. I'm gonna take that as in response to water levels. And this is actually something that Greg Grabus mentioned in his presentation a couple of days ago, which is something that has been used for a long time as an indicator of coastal wetland response to water levels, which is the extent of meadow marsh in a coastal wetland. I think Greg described it a couple of days ago as a canary in the coal mine, where its position on that elevation gradient really tells you a lot about what's going on with water levels in a coastal wetland.
That's very helpful. Thank you, Joe. And Joe, for those of us who may not be familiar, you've already underscored the importance of ongoing wetland monitoring. Apart from coastal wetland vegetation, what other aspects are currently being monitored by CWS or other groups?
Yeah, so I can speak to a number of different things. So we're involved in a binational program. It's actually funded by the US EPA. It's called the Coastal Wetland Monitoring Program. And that is a large scale program that's been going on since 2011 with the very ambitious goal of sampling and monitoring the condition of every coastal wetland in the Great Lakes Basin. So CWS's role in that is largely focused on the Canadian shoreline of Lake Ontario, but that program involves sampling vegetation, water quality, aquatic macroinvertebrates, fish, incidental turtles, birds, frogs, and toads. So there's a lot going on there. That's it's a pretty incredible program that's been going on for a long time now. There are also a number of other large-scale programs, like the Great Lakes Marsh Monitoring Program it's been going on since 1995, focused on marsh bird and frog and toad monitoring in primarily the lower Great Lakes Basin.
That's great. Thanks again, Mike and Joe, for the great presentation and for answering our questions. We will be inviting Mike and Joe to rejoin us for the panel discussion at the end. So please continue to share your questions with us in the Q&A. In the meantime, I will invite Adam to please go ahead and share your screen while I provide a brief introduction. Dr. Adam Beckley is a coastal engineering specialist with the Wisconsin Sea Grant. Adam helps Great Lakes coastal communities build resilience by communicating the latest hazard research, developing outreach products on best management practices, and providing local governments with guidance on planning and preparing for coastal hazards. Adam holds a PhD in civil and environmental engineering from the University of Wisconsin-Madison. And Adam, I see that your slides are up and in full presentation mode, so I'll pass the floor to you.
Thanks, Sharon, and thanks for having me. This has been a great webinar series, and I've learned quite a bit. Today, I'll be talking about one of the outreach products that we've recently developed called Nature-Based Shorelines, Options for the Great Lakes Coasts. I'd like to start off with acknowledging the co-authors on this, Brianna Shea and Jean Clark. This guide came out of a NOAA-funded project that was a collaboration between the Wisconsin Coastal Management Program, the Southeast Wisconsin Regional Planning Commission, Wisconsin Sea Grant, and the University of Wisconsin-Madison. And this project was focused on the 4 southeastern counties in Wisconsin located on Lake Michigan. And I mention that because this is a lot of high bluffs on this coastline, as well as some low-lying areas and a few coastal wetlands. But we were gearing this guide towards our constituents there based on their input, but definitely wanted this to be a sort of broadly applicable guide as well. Right off the bat, if you'd like to find this and follow along, I think a link will be put in the chat, but at least as of now, if you do a web search for Great Lakes Nature-Based Shorelines, you should be able to land on this page and download this guide. So kind of to start off, I'm sure a lot of us have seen this or a similar sort of gray to green spectrum of shore protection. This is from the US Army Corps of Engineers SAGE program, where on the left-hand side, we sort of have our greener, softer techniques for lower wave energy environments. And on the right-hand side are sort of more conventional engineering structures, harder techniques. You may know some of these greener techniques by other names, nature-based shorelines, living shorelines, coastal green infrastructure, NNBF, or engineering with nature program that the Army Corps has that sort of gets more into this green area. Similarly, on the right-hand side, maybe coastal structures, hard armoring, great infrastructure. And this spectrum is a really nice tool to share with folks. But when we were doing outreach on this project, talking to both local governments and property owners looking at options for their shorelines, they were really interested in some of these greener techniques, but wanted to see what that looked like in the Great Lakes, what were some viable options, what were some examples, and also some realistic expectations. A lot of folks knew they couldn't just plant dogwoods on their high energy coast and expect that to, take all of what Lake Michigan could throw at them. So we wanted to provide them with some information about these nature-based shorelines, which incorporate or mimic natural features. So first, what are some of the benefits of nature-based shorelines? And you can kind of see that in this image comparison from Marysville, Michigan, where a steel sheet pile wall was replaced with a marsh sill structure. You know, aesthetic enhancements. The sill structure just kind of, to most people, I think, looks nicer. There's obviously more opportunities for habitat creation or improvement, connecting habitat along hardened shorelines with these types of structures. There can be water quality improvements with the incorporation of vegetation that can sort of clean runoff to some extent. Maybe some easier public access down to the shoreline. And nature-based shorelines can incorporate hybrid approaches where we use maybe some conventional structures and some nature-based elements to suit the environment that we're working in. And in some cases, not all cases, cost may be lower. You know, steel sheet pile is pretty expensive. And if you just consider that because that's all you see around you, maybe you're not getting the lowest cost option with all these other benefits as well. There's also a lot of challenges in the Great Lakes. Our ocean coasts are further ahead of us on nature-based shorelines. And for a number of reasons, we're in a lot of places, particularly in the project site that we're working in, it's a high wave energy environment. We have to contend with ice, of course, the aforementioned water level fluctuations, short growing season, different maintenance needs to conventional structure. And like I mentioned, these are an emerging set of practices in the Great Lakes. They're not maybe folks' first thoughts. So, you know, there's not a lot of examples out there compared to, say, a seawall or a revetment. So that was maybe one of the barriers we were trying to break down with this guide, is sort of illustrate what options are possible in view of these challenges. So this is sort of our summary up front. I won't go into too much detail on this, but we sort of looked at a bunch of case studies and a bunch of options, looking at, you know, guidance from our ocean coasts and try to classify a number of technique categories that we could classify nature-based shorelines in the Great Lakes on. We came up with 6, just vegetation, nourishment, slope stabilization, edging, sills, and then ecologically enhanced hard armoring. And so we kind of compared all these options against each other with a few criteria: environmental benefits, wave energy, the sort of slope that this sort of option can work on, cost, and then maintenance requirements. And I'm gonna now kind of step through each of these options in a little bit more detail. So the first option that we came up with was vegetation. And this is, you know, native vegetation planted along the shore to reinforce the shoreline with roots, dissipate wave energy to some extent, and slow erosive wind and runoff. This is my sort of crude drawing of some of these vegetation zonation figure that we're very familiar with now. And so obviously not suitable option for higher wave energy environments, but sort of our baseline starting with nature-based shorelines. And of course, you can't just plant seed on a actively eroding slope, so it isn't suitable only as the only option on our high slope conditions. But it is definitely part of the portfolio. Our case study here was Bradford Beach in Milwaukee. This was a beach that had suffered a lot of water quality issues. And so they constructed a number of vegetated swales around their stormwater outfalls and then stabilized sort of the banks of those swales with dune vegetation. So getting those stormwater benefits as well as some erosion stability and have it working as a system. And this was on an open coast, but it has a very wide beach in front of it to handle some of that larger wave energy. Our second option was nourishment, placement of clean sediment, which is often sand, on beaches to create dunes, or in the nearshore waters to replace lost sand or build dunes. Oftentimes this has to be seen as sort of a sacrificial placement, and our natural processes, waves and longshore transport, are going to carry it away unless that initial cause of erosion is addressed. I think Pete Zuzek did a good job describing implications about sediment transport and littoral cells yesterday. Sort of the wave energy environment this is suitable for can vary depending on how this gets designed. And our case study example here was Blue Harbor Beach in Sheboygan, Wisconsin. Now, this was a resort that got constructed on the shoreline. And you can kind of see in the lower right here, a revetment disappearing into what looks like a dunes. And so that revetment actually continues underneath the dunes and was buried with sand to create a dune and beach environment. This picture was from 2012 when Lake Michigan was near record lows. And as I mentioned, nourishment can often be seen as sacrificial. This is what happened at high water levels. So that beach sand and dunes got eroded away, but we had that revetment there as a backstop. So to get that back, again, either we'll need to have it naturally replaced or another nourishment to reestablish those dunes. But as opposed to just having that revetment there all the time, there was a period of time where there was habitat and recreational opportunities as well. Moving into slope stabilization, this is where we regrade or reinforce an eroding slope to allow habitat and vegetation to establish. As I mentioned, actively eroding slopes are not great for a lot of species. There's some that thrive there, but you can't just see a vertical slope and expect that to take place. So this is where we have kind of higher slope environments. And depending on if wave erosion at the toe is a big issue, that may need to be addressed as well. So it can really just slope stabilization and lower wave energy environments, possibly need for erosion control at the toe and higher wave energy environments. Case study we had here was the former University of Wisconsin-Milwaukee Chancellor residence. You can kind of see there is the shoreline revetment here, but there was active erosion up at the top of the bluff, encroaching within a few feet of that house. And so what was done here was a vegetated retaining wall. And so you can see they put a staircase over the top of it, but basically not a lot of room to cut that slope back to a stable angle. So rather than sort of building a concrete wall, this was a series of geotextile tubes that were planted. And you can see a nice picture here of the vegetation coming in. You can kind of see that vertical slope there. So a way to incorporate vegetation and additional habitat when a gray option could have been chosen as well. Getting into sort of dealing with higher-ish wave energy environments, we have edging, which is the placement of some material, core logs, wood, stones at the toe of the shoreline to prevent erosion and allow vegetation to establish. This is not for high wave energy environments, but starting to get that into that area where vegetation alone isn't going to be sufficient. Case study here is Shoreline Park in Sandusky, Ohio. This is a relatively sheltered bay on Lake Erie, but obviously you can see before the project there was the effects of some erosion on the shoreline. Another issue was geese loafing in the park and causing water quality issues. So they use core log edging to sort of help vegetation establish along the shoreline, as opposed to revetment, which was also considered. And this helped take care of the goose problem as well, because it cut off their access from just walking out of the water into the park and improved water quality quite a bit. Stepping up again in wave energy, a sill, which is a low profile structure located in the water just off the shoreline, not quite as big as a breakwater, but still able to dissipate some wave energy and create a somewhat quiescent area for a protected marsh or shoreline vegetation to grow. And so I've shown this example earlier. It's the Marysville Living Shoreline in Marysville, Michigan on the St. Clair River. Kind of a big design factor here is ship wakes up and down the river. And so you can see there's this rock sill, some vegetation, and then backed by some rock edging. This replaced the steel sheet pile wall. And so this is at low water levels, and then at high water levels, you can see some submergence, but again, we have kind of those three layers to address the wave energy. Maybe not a functional option on high energy wave environment, but definitely in this more protected area, capable of providing enough wave energy for that vegetation to grow in a much more accessible shoreline. And then finally, what we've termed ecologically enhanced hard armoring, use of vegetation, textured surfaces, other features to kind of work in hybrid with our conventional hard armoring structures to provide habitat and other benefits. So we could see some of these options presented throughout the webinars with wetland cells, the Braddock Bay example yesterday, This can really kind of range, but really, when we need that hybrid option, thinking about where habitat can be added, if we're thinking from shore protection. So, schematic of a breakwater with marsh vegetation or a vegetated shoreline. Some cases where we have revetment, adding upland vegetation has been shown to enhance species diversity in Lake Erie, regardless of kind of the shoreline hardening. It's a good thing to do for habitat. So our case study here is Sam Myers Park in Racine, Wisconsin. This park located right here was sort of behind an old relic breakwater that had been around for decades. Poor circulation in this cell, lots of water quality issues, and of course, Phragmites had kind of taken over the site by 2012. And so what the city started with was raising the breakwater structure here to prevent some overtopping that had been a challenging issue at the site. And then that enabled them to confidently do a wetland restoration and create a constructed wetland at the site. And stormwater is then conveyed through the site and through the constructed wetland to kind of treat the water quality off of the nearby urbanized areas, and the water quality in the embayment has improved dramatically. Lots of species have returned to the site. A really successful demonstration in Wisconsin, at least, of sort of working with those hard armoring structures to really provide some ecological enhancements to the shoreline. So again, here is the summary where we sort of compare these options across those different categories. And just to give you a view of what this document looks like, we have each option laid out, those ratings, an overview, some benefits and challenges, commentary on maintenance, and links to additional resources, as well as photos of examples I didn't cover. Description of those case studies with maps and photos, design considerations. And then also links to other resources we were aware of nature-based shorelines out there, both in the Great Lakes and sort of around the world. With that, I'd just like to say thanks for your attention and acknowledge all the folks who either reviewed or contributed to this guide.
Wonderful. Thanks for the great presentation, Adam. This is such a helpful resource, and the case studies are really wonderful to see. My first question is whether you can elaborate more on the rating of environmental benefits, cost and maintenance requirements. Was this based on quantitative data, qualitative expert judgment, or a bit of both?
Yeah, this I should mention these were sort of all sort of qualitatively rated. We kind of found it hard with the limited number of case studies to kind of put qualitative numbers on it. So it is, or excuse me, quantitative numbers. So it is a qualitative rating to kind of help sort these out.
I think they are helpful, and I'm glad you included cost and maintenance requirements, which is, of course, a common question that we get from practitioners, of course. And as Greg mentioned at the outset, we do not always know how effective some adaptation actions or best practices are once they are implemented on the ground. And based on your research of the case studies, are you seeing these nature-based shorelines living up to their promise?
Yeah, I think, I kind of mentioned at the top is, managing expectations for the conditions we have to deal with. So I guess one example would be the Sam Myers restoration. It did, in 2020, we had a huge storm at record high water levels for January, and that breakwater did get overtopped. The wetland did get damaged, but relatively resilient because it did sort of bounce back. Obviously, there needs to be some reconstruction of that shoreline. There was shoreline damage, but it's still a somewhat functioning wetland, and it's a recoverable situation from an extreme scenario. So adaptive management was huge at that site, and it continues to be.
That's great to hear. Thanks, Adam. And we have a question from Kurt in the Q&A. In the Racine, Wisconsin example, how is the Phragmites treated, and how well have management approaches kept it from regrowing or reinvading?
I don't know off the top of my head how the Phragmites was treated. I do know that the city is very diligent about invasive species removal, and that's another thing to manage expectations about, recognizing that nature-based shorelines take a bit different maintenance than say a hard structure where it's somewhat more routine. So they are very dedicated to invasive species removal, but I don't know off the top of my head specific strategies.
Great, thanks, Adam. And last question before we go to our next speaker, Heather, is now that the guide is published, I wonder if you're looking back, is there anything you wish you included, you or other authors included in the guide, or any new best practices that have emerged since the development of the report?
Yeah, so I think obviously once you sort of put something on paper, all the sort of new developments that come out, there's been emerging case studies, a lot to do with sort of submerged reefs, an example in Lake Michigan, maybe some broadening some specificity on those ecologically enhanced hard armoring. So as those sort of examples come online, we hope to keep the guide updated, and we're working on a story map to sort of help us be a bit more flexible and include more examples as they come up and we learn about them. So a growing field, certainly.
That's wonderful. Looking forward to those resources, and glad to hear that there are plans to update the guide. And thank you again, Adam, for the great presentation. We will be asking Adam to rejoin us at the panel discussion at the end. In the meantime, let me introduce Heather Pankhurst. Heather, please go ahead and share your screen. Heather will be presenting about managing diked coastal wetlands before we go into a quick break. Heather Pankhurst has been the wetland biologist at the Central Lake Ontario Conservation Authority for the past 13 years. She coordinates and implements the Durham Region Coastal Wetland Monitoring Program, DRCWMP, which helps to inform the evaluation of threats and challenges at each coastal wetland, and the setting of SMART goals and objectives for wetland restoration, and provide the basis for monitoring the effectiveness of restoration actions at achieving goals and objectives. And Heather, I see that your slides are up and in presentation mode, so I'll pass the floor to you.
Thanks, Sharon. All right, good afternoon, everyone, and thanks for having me today. I'm going to be presenting on coastal wetland dikes as a management tool, the advantages and challenges that I've seen for a particular case study after having monitored coastal wetlands on Lake Ontario in the Durham region over the last 13 years, and also looking at the last 20 years of data collection. So a diked coastal wetland is a wetland that has been separated from an adjacent lake, creek, or the rest of that wetland by an earthen berm or hard structure. While dike wetlands can be found throughout the Great Lakes, diking is more common in the flat floodplains of Lake Erie and Lake St. Clair, and is more common on the American side of the lower lakes. At least 31% of the remaining wetlands in Lake Erie and almost half of those in Lake St. Clair are diked. Dikes are also common in agricultural areas of the lower Great Lakes where coastal wetlands have been drained in the past for agriculture. Coastal wetlands may be diked for a variety of reasons, in addition to drainage for agriculture, as I just mentioned. In many cases, wetlands were diked to allow for the artificial manipulation of water levels to manage for waterfowl. Other common reasons include to protect wetlands from high water levels and wave action, to remove water quality impairment in degraded watersheds, and to prevent common carp from accessing the wetland. Now let's take a look at a case study, Oshawa Second Marsh, and what we have observed at this diked wetland over the last 20 years of monitoring and management. Oshawa Second Marsh is a 137 hectare coastal wetland located on the shores of Lake Ontario in the city of Oshawa. The wetland is in the Black Harmony Feral watershed, which is approximately 11,000 hectares in size. The predominant land use type in the watershed is agricultural at 42%, followed by natural cover and residential at 23% each. And impervious cover in this watershed is 16%. So these images showed here show Second Marsh in the 1920s after agricultural development, but before most urban development. In 1991, after considerable urban development, but before the dike was installed. And in 2018, once the dike was constructed and wetland management activities have been carried out. There are a number of factors that have been identified as contributing historically to the degradation of Oshawa Second Marsh, including the deforestation of the watershed and subsequent agriculture and urbanization impacts, resulting in increased sedimentation rates and the contribution of excess pollutants, nutrients, and sediment to the marsh, as well as the pumping of dredgeate from Oshawa Harbor in the marsh, which is estimated to be 35 to 70 centimeters of material. The discharge of raw sewage from the nearby water pollution control plant occurred from the 1950s to the 1970s, which contributed nutrients, organic waste, and heavy metals. Alterations have been made to the size and location of the wetland outlet from the marsh to Lake Ontario. CARP have been introduced, and the regulation of water levels on Lake Ontario are all contributing factors. Due to the increasing concerns regarding the impacts to the marsh, a marsh management committee was created that includes representation from the city of Oshawa, who are responsible for operations and maintenance, as well as Ducks Unlimited Canada, responsible for restoration and management activities, the Friends of Second Marsh, responsible for marsh education, interpretive programs, and watershed stewardship, as well as the Central Lake Ontario Conservation Authority, who I work for, which is responsible for monitoring of marsh conditions through the Durham Region Coastal Wetland Monitoring Program. Conditions of concern that have resulted from historical degradation were outlined in the 1992 management plan and included sedimentation high turbidity, altered drainage patterns, reduced emergent vegetation, heavy metals and sediments, a decrease in the waterfowl population, as well as a loss of biodiversity. After considerable work to create a management plan and identify a strategy for implementation, phase 1 was initiated in 1992 and included 12 physical rehabilitation measures. Those included construction of flow deflection islands, reopening of the western outlet to Lake Ontario and closing the eastern outlet, construction of brushbill and floating habitat islands, root wads and crabfish habitats, planting of wetland vegetation, and construction of cell structures for carp protection, etc. So after completion of these measures over the next 8 years, it became clear that the goals of the management plan were not being met. And so phase 2 was initiated, the construction of an earthen dike. This phase included the implementation of 3 management strategies. The first, to reroute Harmony Creek to bypass Second Marsh and outlet directly to Lake Ontario. The second, to close the existing outlet and install a 2-way pump to allow for active water level management. And the third, to install a fish control structure to prevent adult common carp from entering the marsh to spawn. The advantages of rerouting Harmony Creek were that sediment inputs from the watershed were reduced and water quality was improved in the marsh. However, this management activity has presented many ongoing challenges. The loss of hydrologic connection to the watershed and the resultant loss of coastal wetland functions such as flood conveyance, flood storage, sediment transport, and nutrient cycling. Altered hydrology and water chemistry, the loss of flow through the wetland results in higher temperatures, decreased oxygen availability, nutrient loading, and the accumulation of organic material that would have been flushed from the wetland. It also does not address historical sediment deposition and ongoing organic material accumulation that have created shallow conditions and no deep water areas to serve as refuge for fish or to provide habitat for muskrat in the winter, and have also limited the seed bank. Biological connectivity has been greatly reduced and access by fish and inverts is thereby limited. And biological diversity has been reduced. A cattail monoculture predominates with Phragmites monocultures present in various areas as well. And plants and animals that require a dynamic wetland boundary are limited. The ability to manage water levels in the marsh allows for drawdowns to mimic historical low water level conditions, which do not often occur under the current water level regime in Lake Ontario. Drawdown conditions encourage the germination and establishment of aquatic plants. They consolidate sediments and improve water quality conditions. And while the ability to manage water levels is advantageous, it presents many challenges for implementation. It requires a substantial amount of money, resources, and planning to install and maintain the infrastructure required to manipulate water levels, as well as staff commitments and time to accomplish a drawdown. Beyond the resources required for a single year drawdown, it would be impossible to implement management to the extent necessary to mimic historical water level fluctuations. It's also not possible to plan for low lake levels and appropriate years for drawdowns. Once a drawdown is initiated, high water level years can render drawdowns unsuccessful. Drawdowns can unintentionally encourage the spread of invasive species such as hybrid cattail, Phragmites, and European frogbit, especially if the seed banking conditions are not suitable for native plant establishment. The dike, in addition to development around the coastal wetland, provide no space for wetland expansion during high water level years, causing the wetland to become flooded out and the loss of meadow marsh communities. In addition, obtaining permits for the installation of coastal wetland dikes is necessary, and given the associated impacts, these may not be granted. The installation of a fish control structure allows for the reduction of the adult common carp population and reduces disturbances caused by carp during spawning, including the uprooting of aquatic vegetation and the resuspension of sediments, which create turbid conditions. The design of the fish grate and the timing of its employment must be carefully considered to restrict adult common carp while allowing native species to access the marsh for feeding, spawning, and nursery habitat, as well as to prevent other wildlife from becoming trapped within the structure. We must also educate the public on the function of the fish grate. Many people have trouble understanding, or they may disagree with why we are preventing carp from accessing coastal wetlands. And we have had individuals remove the carp gate at this marsh in the past to allow carp to enter. It only takes one incident of that happening to undo years of work. Now let's take a look at the results of our monitoring data. Oshawa Second Marsh is monitored as part of the Durham Region Coastal Wetland Monitoring Program, and the attributes we measure are listed in the table and are representative of the condition and health of our coastal wetlands. Water quality, submerged aquatic vegetation, bird, fish, and aquatic macroinvertebrate communities. For each of these attributes, we use an index which combines multiple characteristics of that attribute to give the wetland a health score between 0 and 100. These are the results we have seen since monitoring began in 2002, following the installation of the berm. The data show short improvements in indices following each drawdown. However, we see indices then begin to decline within 1 to 5 years. As part of CLOCA's watershed planning process, we have identified a goal of an index value of 60, which we believe is achievable and represents good health for coastal wetlands in highly urbanized watersheds. At Second Marsh, fish and water quality have not met the goal in any of the years we have monitored. Invertebrates have met the goal in 1 year following the 2004 drawdown, and birds and submerged aquatic vegetation have met the goal for several years following each drawdown. We will, however, need a few more years of data following the second drawdown before we can get a clearer picture of how things are responding. The wetland has filled in substantially with cattails and has difficult to access for monitoring everything except birds, which is reflected in some of the lack of data points you see there in the graph. Overall, the main lessons learned at Oshawa Second Marsh, from my perspective, are that the diking of Oshawa Second Marsh and associated management activities have achieved emergent vegetation regrowth and some improvements to marsh conditions, as reflected in the ecological attributes we have measured. However, improvements have been short-lived, and we have yet to meet our wetland health goals. Dikes require a significant amount of funding, effort, and time to establish, maintain, and to continue ongoing management activities. And this must be kept in consideration. Historical sediment deposition and the lack of hydrologic connectivity are limiting to wetland health at this location. Despite the dike and associated management efforts, oxygen depletion, vegetation monocultures and invasive species, shallow water, excess organic material, and fish access challenges are ongoing. When considering the installation of a dike at a coastal wetland or how to manage an existing dike to wetland, I would recommend that you be aware of and consider the limitations and impacts of diking coastal wetlands when considering this option, that you address historical impacts if possible before installing a dike, such as sediment accumulation, that you have a plan to address the future impacts of the dike, such as vegetation monocultures, organic material accumulation, water temperatures, and oxygen depletion, that you create a long-term plan with clear roles, responsibilities, and funding requirements, including infrastructure maintenance, drawdown triggers, staff responsibilities, and adaptive management, that you utilize water levels to your advantage. For example, try to set up in the best way possible so you can complete drawdowns more easily in low water level years, and consider maintaining higher water levels in the winter for muskrat, as these populations provide natural management of cattail monocultures. And also ensure biological connectivity to the greatest extent possible through the location, design, and use of control structures. That concludes my presentation for today. Thank you, everyone, for listening.
Great presentation, Heather. You've so helpfully laid out the advantages and challenges in your presentation from a biologist's perspective, which I find is very helpful. I wonder, in what situations do you think the creation of new dikes makes sense?
Well, I think it's really so location dependent. If there are, you have to weigh the benefits versus the impacts or challenges for that diked wetland. So I don't know that I could say definitively where one should occur or where shouldn't. I think that you really have to come together as a team and make all those considerations and make sure that you have really followed a process for planning so that if this is the only option we have and that we think we can make improvements, then that may be necessary. But a lot of times we're quick to jump the gun and install that without thinking all the different options through.
That's great. Thanks, Heather. And I think your recommendations are certainly very helpful for those considering this option. And another question is about Oshawa Second Marsh. What more will it take to reach your wetland health goals for Oshawa Second Marsh? If you had unlimited time and resources, what more do you think needs to be done?
Oh, if I had unlimited time and resources, though, I don't know. There's so many things that you could do. I think one of the big things that really needs to be addressed here is the historical sediment deposition and the ongoing organic material accumulation. We really have shallow conditions there. We don't have those deep water refuge areas. There's not a lot of, and which causes, higher temperatures and oxygen depletion, which is really limiting to wildlife populations there. As well as when we do a drawdown, we see primarily hybrid cattail coming in and taking over. So that's showing us that there are some limitations in the seed bank as well. So I think addressing that would be, in my opinion, one of the biggest contributions we can make to this wetland. But it's really a group effort, and we're a part of a management committee. So we're working on updating our management plan and going forward with new looking at our management strategies and how we can make changes going forward. But it's an ongoing process for sure.
That's great. Thanks, Heather. And we had a question from Greg, whether any of the monitoring results for Oshawa Second Marsh have been published.
So we have a story map where all of our integrated watershed monitoring data and our indices are available online for all of our different monitoring programs. So I can share that link to the story map. But it does create, it's hard to publish data when you're monitoring annually because, the data is always being updated and changing. So by the time you publish it, that data is out of date. So we're trying to move towards more of a story map situation where the data is available, year by year, and we're still working towards that as well. But you can always contact me for our data for any of the Durham Region coastal wetlands.
That's great. Thanks, Heather. And we do invite you to share a link to the story map during the break when we go to that next. We do have two questions in the chat from Amanda and Jeff on muskrats and carp barriers. Amanda is wondering if you have any issues with muskrats burrowing through the dike walls, and if so, how you manage it. And Jeff is wondering about the present status of the carp barrier.
So I don't think we've had challenges with muskrats burrowing through the dike, but the dike has been several years ago, because it was a lot of organic material that had been used for the dike. They did have to reinforce the dike, and a fair amount of money was spent on that. So at this point, no, we haven't seen that as a concern. But once again, one of the challenges is that low water levels in many of our coastal wetlands in the winter are really limiting to muskrat populations. And then, sorry, the second question was about the fish control structure.
It was about the carp barrier, yes.
The carp barrier, yep. So it's been reinforced to prevent vandalism, being removed in the future. And The spacing has been adjusted, to maximally allow other fish species in and keep adult carp out. And what else can I say about the structure? And then the grade is, we try to time that so it's put in so that pike can get in beforehand, and then we put it in before the carp are really coming in.
That's wonderful. Thank you so much, Heather, for the great presentation. In the interest of time, we will now take a 5-minute break. So let's take a 5-minute break to refresh before our last set of presentations before the panel discussion. And we are back. Our final 3 guest presentations will help extend our focus on invasive species management, starting with Marianne and Dominic. Dominic, please go ahead and share your screen while I provide a brief introduction. Dr. Marianne Bachand is a project coordinator in the hydrodynamic and ecohydraulic section of the Meteorological Service of Canada, and Dominic Thériault is a modeling project officer within the hydrodynamic and ecohydraulic section of the Meteorological Service of Canada. Marianne and Dominic, welcome back to our webinar. I see that your slides are up and in full presentation mode, so I'll pass the floor to you.
Thank you, Sharon. I'm glad to be back. So to evaluate the impact of climate change on the invasion potential of cattail and Phragmites in the Great Lake, several models that allow to link the physics, the topography, and the vegetation are needed. So we use an integrative approach called the Coastal Wetland Response Model, known as the CWRM, that was the subject of a previous presentation earlier this week. So the CWRM is a spatiotemporal data layers collection. And today we will present modeling results regarding cattail and Phragmites in 20 wetland sites across the Great Lakes. But we want to bring to your attention that to have those results, we had to also model the physics, so hydrodynamic and waves, create DEMs, and model the wetland class succession. You have on these slides the names of the people that worked to make this possible, and we want to acknowledge their contribution in the results that Dominic and I will present to you today. We also want to let you know that our chief section, Dr. Jean Morin, will join us for the questions session and the later panel. So the modeling effort, like I said, is across 20 sites in the Great Lake. Sites were selected for the hydrogeomorphological type, status, local or indigenous interest, and data availability. Through the presentation, we will show you general modeling results for every site and specific maps for sites. Just know that those specific maps are available for every site and can be provided to you later. Okay, so for now, like we explained last Monday, the CWRM includes one carbon emission scenario called RCP 4.5. It's a moderate carbon emission scenario. It represents a weak mitigation of our CO2 emission in the future. This RCP has been run with different global circulation models. Due to time calculation, only 2 simulations were done that will be called lower and upper bound scenario in this presentation. Under the lower bound scenario, the blue line in your screen, water level by the end of the century is similar in terms of mean and interannual variation compared to the recent modeled past. Under the upper scenario, the orange line on the right graph, water levels are higher by the end of the century and much variable from year to year. So when an invasive species does not fully occupy its ecological niche, it is difficult to dissociate the effect of climate change from its natural growth, its potential to invade. So to answer that challenge, we use 2 types of model in our modeling approach. The first type of model is called population growth model. It's simulate Phragmites and Typha expansion due to their natural characteristic and their impact on wetlands. The second type of model is called suitable habitat models. and it explored the effect of climate change on Phragmites and TIFA on spatial distribution of their suitable habitat. It kind of answered to the question, is there better condition for the establishment of the two invasive species under climate change? So population growth models simulate different life stage and growth mechanism based on the biology of the species. We are looking right now at the model for Phragmites. So for a node of the CWRM grid, for a node to be classified as invited by Phragmites, it has to go through different stages. The first one to go from no Phragmites to seedling, certain condition to allow germination need to occur. For example, a specific water depth. To go from seedling to adult stage, seedling has to survive facing various water level conditions during that time. After 5 years of suitable condition, the adult stage moved to colony through seed dispersal. And finally, a colony can colonize neighbor nodes on the CWRM, also by vegetative propagation. So we use a similar approach for the expansion of TIFA. I will not go through all the stage here, but the main difference for cattail here is its ability to accumulate litter through time and ultimately creating floating mats that are no longer influenced by the water level regime. Okay, so this is an example of the PGM's result. It's an example of a result for the population growth model on the calibration side. I'm really sorry, I'm not sure I can pronounce it right, but thoroughfare, that's really hard for a French speaker. So on the map, Phragmites is red and TIFA is orange. So following the high water level of 1985, most of this wetland is flooded and the TIFA distribution is sparse. Following the receding water levels of 1997, the Phragmites began to expand in Lake Erie wetlands. And in the map of 2015, you can see that Phragmites are much more abundant among TIFA and in shallow marsh in general. So our model will produce accurately both observed years, depicting an accurate portrait of the growth and how fluctuating water level affect both species. So moving to suitable habitat model, here you have the suitable habitat of Phragmites on the left map. Maybe the suitable habitat distribution may be much larger than the current habitat that you see on the right map, since the species is relatively new in the system and does not occupy fully its ecological niche. So change in suitable habitat between the recent past and future period allow to understand how climate change affect the invasion of the species. How did we develop a suitable habitat model? So a model for each species is calibrated from observation across many wetland sites. Wetland observation comes mostly from remote sensing. The calibration is done through a random forest model that use wetland observation as dependent variable and physical variable as predictor. The physical variable are, for example, bottom slope, water depth, dry wet cycle, and are calculated with the physical model included in the CWRM. The validation is done with a subset of the wetland observation. The two models, the one for Phragmites and cattail, have an accuracy greater than 80%, which is high for this kind of model. We then run the model under the lower and upper bound scenario water level time series to be able to compare the simulated recent past of those species distribution with the simulated future in order to identify the range of possible change in the distribution of the suitable habitat of both species. I will now let you with Dominic, who will show you the results of those models. Sorry.
All right, thank you, Marianne. So I'm going to present the results for the 4 lakes, or Lake Ontario, Lake Erie, Lake St. Clair, Lake Huron. And so we're going to present present an example of the population growth model for one site, the result for both models for all sites in this lake, and the general conclusion for a lake. So here we're in Lake Ontario. On the left side, you have the distribution, predicted distribution of the Phragmites and the Typha versus the time. So we see here that the Phragmites is expected to be about twice more abundant with the upper bound scenario than the lower bound. So the upper bound scenario is the orange line and the lower bound is the blue. And for Typha, the model predicts a similar invasion for under both climate change scenario. So with the lower bound scenario, on the upper left figure, we see the distribution for Typha and Phragmites in 2008. We see that it's mostly Typha that is abundant, but at the end of the century in 2098, the Phragmites are much more abundant along the shores. With the upper bound scenario, we see that the Phragmites are also establishing in Lake Ontario, but at much higher elevation since the water level went higher. So first, we're going to look at the results of the population growth model. So those results are the carrying capacity projected by the population growth model divided by the wetland area. So it's a percentage of the wetland that is invaded. The black line is the possible range of the climate change scenario, and the green bar is for the lower bound scenario, and the orange bar for the upper bound scenario. So here we see that the Phragmites is expected to invade more with the upper bound scenario, around 20 to 50%. And with the lower bound scenario, it's around 10 to 20%. For the Typha, it's around 20 to 40% according to the scenario. So for the suitable habitat, so we answer here how our climate change increasing the suitable habitat of the species. Here we see that for the upper bound scenario, almost all sites are increased. The climate change favors the Phragmites expansion with the higher levels, and with the lower levels, it increased in two sites in South Bay and Airport Creek. But for Typha, it's more site specific. So there's a decrease of Typha in two sites and with the upper bound scenario, and an increase in two sites in Lindy Creek and Airport Creek also. And with the lower bound scenario, there's a 3 sites that the Typha is increased. So for the upper St. Lawrence River and Lake Ontario, higher lake levels will likely favor invasive species. Climate change will play a role in the expansion of both invasive species. The condition will improve for Phragmites with the upper bound scenario, becoming more abundant than Typha in some sites by the end of the century. Without significant change in mean lake level and interannual variability, as presented by the lower bound scenario, Typha will likely remain dominant in Lake Ontario. And overall, the distribution of both species in all sites pose a threat to wetlands, although Phragmites is not currently widely established on the shores of Lake Ontario. So I'll go quickly for the other lakes. Here we have the result for Rondeau Bay. We see that with the lower bound scenario, the invasion is much larger. Mostly the shallower wetland is invaded by Phragmites in red. Whereas with the upper bound scenario, this shallower wetland is mostly flooded, and there's some Phragmites stands along there and some Typha, but we see that what happens is that there's a big migration of emergent marsh in the swamp, where the Typha established and also the Phragmites. So in Lake Erie, we see that it's the lower bound scenario that seem to be where the Phragmites are much more abundant than the upper bound in all sites. For the Typha, similar conclusion can be drawn except in Grand River Mouth. And for the suitable habitat, it's site specific. For example, in some site, the lower bound scenario seems to increase the Phragmites. And in other, it's the upper bound that seems to increase, such as Grand River Mouth, and the upper bound also decrease the suitable habitat for Phragmites. For Typha, the upper bound scenario seems to decrease the Typha suitable habitat, and the lower bound seems to increase it into 3 sites. So lower water level will likely favor the fragmate expansion. Climate change will play a role in the expansion of phragmites in Fox Creek, Long Point, and Selkirk Provincial Park. In Rondeau Bay, we saw that the wetland was heavily invaded by phragmites, but under the lower bound scenario, we see our modeling project that this invasion is related to the exponential growth of the species. So it's the climate change are not increasing the suitable habitat for the species, and with the upper bound scenario, they're decreasing the suitable habitat. Under the upper bound scenario, the upper bound scenario is favorable for typha in most sites except Grand Vermouth, and all wetlands are treated by both invasive species. Climate change will favor the expansion in specific sites. So now let's look at what happens in Lake St. Clair. It's similar to Lake Erie with the lower bound scenario. Almost all the wetland is invaded, even in the open water area. And with the upper bound scenario, the wetland is mostly flooded and it's not suitable very much for the germination and establishment of the species. Typha is able to establish a little bit in the higher elevations, but the phragmites are almost non-existent. Here it's interesting to see on the phragmites in the graphic typha graph, where we see the typha going down from about 2040, it's where the phragmites are increasing. So there's a relation in the model that an interaction between the phragmites and typha in the model, where the phragmites can take over the typha, but the typha cannot take over the phragmites. And that's what we see here. So a quick overview for all the sites in Lake St. Clair. With the lower bound scenario, all the sites are heavily invaded by phragmites, and with typha also it's more invaded. But with the upper bound scenario, the upper bound scenario is more favorable for typha than phragmites. For the suitable habitat, all sites are the suitable habitat of phragmites are reduced under the upper bound scenario and increase in St. Clair and the Trois River Marsh. But in Johnston Bay, the heavily invaded site we saw, it's not the climate change that caused according to our modeling, it's not the climate change that caused this invasion, it's the natural growth of the species. When it's not controlled, because our modeling does not take into account the control. And the typha, for the typha under the upper bound scenario, the suitable habitat is reduced in all sites. So in Lake St. Clair, the lower water level will likely promote the phragmites in most sites. Yeah, as I mentioned, the climate change will play a role in phragmite expansion in the Trois River Marsh, Lake St. Clair, and will not play a role in Johnston Bay. So here we have some results for Lake Huron. I'm running out of time, but we have phragmites along the shores mostly with the lower bound scenario, and with the upper bound scenario, the wetland is mostly flooded. There's some phragmite stand that occurs in slightly higher elevations. So for Lake Huron, the results are mostly site-specific, but overall, the suitable habitat is decreased with climate change, except in Francis Point and for typha also. I won't go in all the sites because I'm running out of time. Overall, the climate change reduces the suitable habitat area for both invasive species in all sites, at the exception of Francis Point. The expansion of both species is related to their natural growth. With the exception of Baie du Doré, Lake Huron sites are not currently widely affected by invasive species considered here. Despite the simulation results, phragmites and typha invasion should be monitored in Lake Huron, and management is encouraged to protect the biodiversity and ecosystem integrity of the wetlands in this lake. So we'll end up with some highlights for all the lakes. So what we conclude is that the lower water levels will likely favor the phragmites growth in all lakes except Lake Ontario. with the lower water levels, typha should stay dominant in Lake Ontario. High water level reduce the growth and suitable habitat of both species in Lake St. Clair. And in Lake Huron, wetland sites generally appear less vulnerable for Phragmites and typha invasion. Climate change is a trigger for both species invasion in some sites. It depends on the climate change scenario, but we saw that the species in itself are also the reason for invasion. So we want to thank you. It was a big team that worked on this project. For more details on the presentation of the coastal wetland response model, you can refer to our presentation from April 4th. Thank you very much.
Wonderful. Thank you so much, Marianne and Dominic, for the great presentation. Now I'd like to invite Marianne back, and also we are fortunate to be joined by Dr. Jean Morin, Section Chief of the Hydrodynamic and Eco-Hydraulic Section of the Meteorological Service of Canada. So my first question is whether the population growth model and suitable habitat model be used to model the response of other invasive species. Perhaps Marianne, if you wanted to go first.
Not in our, we use the suitable habitat model for cattail in Rainy and Namakan system that is shared between Minnesota and Ontario. But it was the first time in our team that we were using population growth model for invasive species.
That's great. It's certainly very interesting. Dominic and Jean, did you want to chime in as well?
I think we could use population growth model for other species, but we have not yet. But we would have to do other function, like to modify the function to adapt specifically to the species and also calibrate with the observations.
That's great. And our next question is recognizing that, of course, no model and modeling is perfect. What are some benefits and drawbacks of using the two models?
Well, it's hard to like make a model that is perfect everywhere. It's really hard. Like we had some very accurate results, like in a site, for example, in Thoroughfare, but like in Lake Ontario, we tried to use the same model, and like we wanted there's almost no Phragmites in Lake Ontario, so we wanted to have the model that predicts no Phragmites. So it's hard to have a model like a population growth model where its function, its threshold that is good for everywhere. The suitable habitat model is way much easier to calibrate. It's used with wetland observation, absence and presence data, so it's fairly easier to calibrate.
Do you want to go, Jean?
Oh yeah, I can go. Yes, so the accuracy of models, it's quite simple. It's you need good data to start with. So you need tons of data from the plant's perspective observations, and you need good physical data. And the difficulties, the biggest or the largest problem we have is accurate DEMs. It's very difficult to get the right ground elevation. It's when you go, if you ever walk in a wetland, you go there and determining the exact location of the ground is a difficulty starting with. So there is a basic uncertainty in the measurement itself. And then if you don't have that accuracy of 10 centimeter, you send garbage to the modeling. And yeah, so that's the most difficult portion, is to get ground truth to correct DEMs that are not perfect, basically because the LiDAR is measuring plants, leaves, not directly the soil or the ground. And then we need tons of plant data. The more you have, the better the model is. So basically, just question of data.
So I think Dominic and Jean focus on the difficulty of the modeling, but what is beneficial, because I just want to remember you that we have an accuracy of 80%, which is kind of pretty amazing. It's that you can compare scenarios of decision. Let's say we take this decision. What's going to happen with the cattail? What's going to happen with the Phragmites? And you have the same error in all the scenario that you're making. So you are able to compare those scenarios and to take quite good decision of moving forward.
That's wonderful. Thank you all for those great points. My last question before we move on to our next speaker, Heather Braun, is how would you like to see this data used to help manage Phragmites and cattails for those wetland sites? Perhaps we'll start with Jean.
Yeah, so yeah, it's good. It's a good question. It's the model can be used as a predictive tool to determine which wetlands is most vulnerable to invasion, and then if the control can be direct, so removal, mechanical removal or chemical treatment, but then there is this possibility of managing water level in a different ways. So this is where modeling could be very interesting to use, and in the long run, this type of model could be used in the regulation process, determining the right way of managing the levels in the large lakes. So it's going to be used. So next year we have a project of adapting this model in a simplified manner for the GLAM committee to introduce these concepts into the management plan for the Great Lakes.
Very interesting. Thank you, Jean, and looking forward to that future work. Marianne and Dominic, anything you'd like to add before we go on to Heather?
If I can build on what Jean said, it just regarding cattail, it was a really fast presentation, but cattail can create floating mats where even using water level management at this point will not be possible. You know, we're going to change the water level and the mat will just change its position. So it can help to identify where other action should be taken. So like, let's say burning the cattail, or I'm not used to manage other action that can be done, but we can identify where and in which wetland you should act, because you have no more control regarding that problematic.
That's great. Thank you, Marianne and Dominic.
I think it would be fun to maybe model the Phragmites and cattail, but in a more restrained site with very good observation data and initialization point. So like we map the Phragmites where they are right now, and we project where they could be in the future with the different weather level management scenario. So I think that would be a very, very cool thing to do.
Wonderful. And a big thank you to all of you again. And we look forward to hearing some reactions from our next speakers as well to this modeling result. So next we will hear from Heather Braun, and I will just briefly introduce Heather and invite Heather Braun now to please go ahead and share your screen while I provide a brief introduction. Heather Braun is a habitat biologist in the stewardship unit of the Canadian Wildlife Service in Ontario, where she coordinates the Phragmites management program and supports landscape planning and implementation. She holds a master's in natural resources management degree focused on wetlands and waterfowl, and a Bachelor of Arts degree in psychology and zoology from the University of Manitoba. Welcome, Heather, and thanks for joining us. I see that your slides are up and in full presentation mode so that you're all good to go.
Excellent. Thank you so much, Sharon. She's just been an amazing moderator. So I just want to give a big shout out to Sharon here for all the work that she's doing. And then thank you all for the opportunity to present in this webinar series. It is really great to hear from other speakers working in the same sphere and continuing to sort of connect the dots in terms of our work. Today, I will be talking about the large-scale management of invasive Phragmites in the Long Point on Lake Erie. This is the largest Phragmites management effort that has taken place in Canada. And Phragmites management is a strategy that we're implementing to restore diverse ecological systems in the Long Point area. And I've tried to look at this also through a bit of a climate lens. And so I think it's important to recognize that invasive species management and Phragmites management in general is an important strategy to enhance the adaptive capacity of wetlands. So just an overview of what I will be presenting on today. I just wanted to talk a little bit about Phragmites. I'll probably glance over some of that since I expect most of you are fairly familiar. I'll talk a little bit about the ecological impacts as well as sort of the climate impacts of Phragmites, and then get into the Long Point Region Phragmites Management Program, our monitoring and outcomes, and our next steps and opportunities. So I did want to include a couple of images of Phragmites that I took from the air a few years ago at Long Point, because it is just occurring on a massive scale. And you can tell from the light green in these photos, this is the extent of Phragmites. And so while we often see frag occurring in roadsides and along the highways and that sort of thing, the scale of the infestation in the Long Point area is really significant. So frag is considered the most aggressive invasive species and Canada's worst invasive species. It's a perennial grass. It grows generally up to 5 meters tall, except in Long Point, where it can grow up to 6 meters tall, which is also the height of my house. It grows extremely densely, both above ground and below ground. And you can see here some of the images, both above and below ground. It has no native predators, and it has high phenotypic plasticity, which means it can tolerate a range of ecological conditions that allow it to thrive under conditions that most native species cannot. So I also wanted to point out that there is a native species of Phragmites that occurs really throughout the same range, but it grows differently. It's much more of a happy neighbor. It grows much more sparse than the invasive species. But when we're managing, we're always cognizant that there is a native species out there. So Phragmites itself is a very resilient species, but its ability to dominate across multiple habitat types reduces the resiliency in our coastal wetlands. And so in general, because of their ability to adapt to conditions caused by climate change, invasive species have severe consequences for wetlands and are a threat to coastal wetland health. Phragmites itself outcompetes native species and results in a loss of biodiversity and habitat, notably in this area for species at risk. It also impacts nutrient availability, has been seen as a source of greenhouse gas production. And so, you know, it's just frag. Frag is not something that I like to have as a constant challenger. So the Long Point region, as you've heard from many other speakers, is just a really special and unique area. It has an incredible pedigree of international recognition as a World Biosphere Reserve, as a Ramsar wetland, as a globally important bird area. It is also home to 2 national wildlife areas, a provincial park, and crown lands, as well as parcels owned by Birds Canada, the Nature Conservancy, and historic hunt clubs. So it is, compared to many areas along Lake Erie, a really relatively unaltered system. It provides habitat for more than 80 federally listed species at risk. And you'll see here I've delineated the upper watershed portion of Long Point. This is an area recognized by the Canadian Wildlife Service as a priority place for conservation action. And you'll note that when we look at management of Phragmites, we're not just looking at the areas on Long Point itself, but also those areas of upper watershed that eventually drain. into the lake and the wetlands. So as was just noted, there has been a large increase in the expanse of Phragmites that occurred through the early 2000s, likely exacerbated by low water levels. So as an example, this image is our Big Creek National Wildlife Area. In 2006, there was about 5 hectares of Phragmites at this site. And by 2015, we were close to 176 hectares of Phragmites. The image on the right is all of the mapped Phragmites within this area, which was originally estimated to be about 1,300 hectares. And now we're looking at more like about 1,800 hectares. So by about 2015, the extent and spread of frag was really significant and was considered an imminent threat to multiple species at risk and other wildlife. And it was apparent at that point that immediate action was necessary to address this threat. However, in Canada, we didn't have all the tools we needed to be able to manage Phragmites on this scale. So that gets us into talking about Phragmites management itself, which is a science and an art. So in order to manage Phragmites effectively, an integrated pest management approach is required. And this means that we rely on several management techniques used in combination and over time. So in the US, a suite of science-based pest management practices had been studied and applied since the early 2000s. And generally, this includes application of an herbicide, often in the fall when the plant is transferring energy down to its roots. And then in the winter, there is mechanical management of standing dead to knock down those plants, which would otherwise remain standing for multiple years. And of course, ecological monitoring occurs throughout, and you don't finish after 1 year. You continue to go back the following season, the following fall, and continue to do retreatment with herbicide. However, this pest management practice could not be implemented in Canada because we did not have a registered herbicide for use in aquatic habitats. And so for a long time, the frag at this scale was really just allowed to continue to expand to sort of that tipping point. So in 2015, a large group of partners came together, led by the Ministry of Natural Resources and Nature Conservancy of Canada, including 20 plus other regional partners, including Canadian Wildlife Service. And they wanted to initiate a pilot program that would use science-based pest management practices that relied on the use of a water-safe herbicide to treat Phragmites in the Long Point region. The purpose of the project was to recover wetlands, wildlife, and species at risk by managing Phragmites, conducting ecological monitoring to evaluate both the management techniques as well as the outcomes, and to encourage the collective action on Phragmites management in general. This project required special authorization from the Pest Management Regulatory Agency of Health Canada to get approval for the use of the herbicide, which was Roundup Custom. It's a glyphosate-based herbicide that is not combined with a surfactant. We combine it with a water-safe surfactant, and that's what's been approved for use. This also required some direct engagement with Monsanto, which is now Bayer. And so you can imagine that was a little tricky. And another point to note is that the use of this herbicide was restricted to the Long Point region and specifically to the holders of the emergency registration, which was the Ministry of Natural Resources and Forestry, and ultimately the Canadian Wildlife Service. So this was considered a fairly high risk project, the first of its kind, and that's why we referred to it as a pilot. And so in association with the implementation, we also implemented a large ecological monitoring plan to ensure the effectiveness of the best management practice and that outcomes for habitat and wildlife were as expected. And we also wanted to demonstrate the safety of this management practice, both for the public and for aquatic systems. So the ecological monitoring that we conducted included looking at assessing the impacts of Phragmites management to species at risk and species at risk habitat, assessing the effects on Phragmites itself, the efficacy of the treatment, as well as looking at potential impacts to non-target vegetation, looking at what vegetation will return after treatment. With respect to the use of the herbicide, we were looking at the exposure risk of the herbicide glyphosate and its breakdown products, and the surfactant in water and sediment. And we also looked at the effect of the management on wetland biota, including marsh birds, herptiles, and fish. And then we've done a bit of monitoring on the effects of fish habitat, and also working with the local health unit, looking at the impacts of the application of an herbicide on drinking water. And so you'll see in this image, the Phragmites on the left is Phragmites that was treated with an herbicide. Looks pretty dead, whereas the stuff on the right was untreated. And so we're happy to report very good success so far. So from 2016 to 2019, the project was started on a large scale by the province and Nature Conservancy Canada. And they initiated this work basically from 2016, 17, and 18. And they managed just hundreds and hundreds of hectares of Phragmites. As you see from the map, the areas in red are those that were treated, and the areas in yellow are untreated. Basically, there was one landowner that was not participating at the time, and that was the Canadian Wildlife Service. And we found that we had about 700 hectares of Phragmites on the national wildlife areas, and that if we didn't begin to manage those areas, they were prime areas of sources for reinvasion and thwarting the overall program. So you can see from the photo on the bottom right, the area on the left is Long Point Provincial Park. It has been managed, whereas the area on the right is the thoroughfare unit of Long Point National Wildlife Area, which has not yet been managed. And so in 2019, the Canadian Wildlife Service did start a management program using that same best management practice, and also being sure to avoid critical timing windows for species at risk and other wildlife. And we have continued to monitor and adapt using the same sort of approach. We've also used specialized contractors, primarily the Nature Conservancy and Giles Restoration, to do this work. They are not typical maintenance contractors. They're very specialized in habitat restoration, and have been excellent partners for us. To date, we have managed approximately 360 hectares and have about 250 to 300 hectares planned for this fall. Thereafter, I have a little asterisk because this is likely our last year of being able to use the herbicide Roundup Custom, that glyphosate product, because the herbicide Habitat Aqua, which is imazapyr based, has now been approved for use in Canada. And it's a bit of a different bird, and we can talk about that offline, but we hope to use that on a smaller scale during retreatment efforts in 2024 and thereafter. You'll see here, we did use a helicopter to treat our Phragmites, which was important because we were in very remote areas. And then we've also used a Marshmaster, which is a large aquatic tracked vehicle, to treat Phragmites, as well as to manage that standing dead vegetation over the winter. In terms of our monitoring results, We've been working with Rebecca Rooney's lab at the University of Waterloo. They have been doing ecological monitoring for both CWS and the province since 2016. Results to date are favorable. We're finding the efficacy of the control is very high. So over 4 years after treatment, we're still seeing more than 95% reduction in live stems. And we're starting to see native vegetation occurring. The first couple of years that Rebecca's team was monitoring, we saw a bit of a surge of secondary invaders such as European frogbit. But as the project has continued and as water levels have changed, we're now starting to see native plants resurging. And so that's really excellent to see. I'd also like to report that we're not seeing impacts to non-target species. Our herbicide concentrations in water and sediment have always been far below levels of concern for aquatic organisms. We've never had an issue with there being too high a concentration of the herbicide in drinking water. It's always been significantly below Ontario drinking water quality standards. And we're seeing open water and hemi-marsh conditions starting to return, as well as recovery of vegetation, including some SAR species. So overall, we're starting to see some really favorable results from the project. But one of the exercises that we've done is to work with Morgan, who presented earlier this week, and Lori White and their team at the Science and Technology branch to do some satellite imagery analysis. And this work also began as a bit of a collaboration with Pat Chow Fraser's lab at McMaster University. So we have a permit requirement to map and quantify the change in available fish habitat through the conversion of Phragmites to open water. And so using high resolution satellite imagery, you'll see on this aerial imagery, there's like the chunks of Phragmites in these light green, which are represented in red in the 2018 map, and then are largely all but gone in the 2020 image. And so we're seeing that 1 year post-treatment, or in this case, I guess the image on the left is 2018, we are seeing that the areas that were Phragmites are now replaced with more open water and floating vegetation. So our next steps in this project, of course, we still have a couple of years of management. We're going to continue to do some seed bank analysis and to look at what native species can encourage resilience in the wetland. What is the value of these species to wildlife? And we're starting a new research project to look at vegetative forage quality for waterfowl. We want to look at the role of water levels in the invasion cycle and continue our long-term veg and wildlife monitoring. We have a SAR turtle telemetry project ongoing and continue at the large long point scale to look at satellite imagery and evaluate the overall change in habitat. Implications for climate resilience. So this project should increase species diversity, increase that the habitat that's available for both plants and animals, and result in increased habitat for species at risk. It should also help restore other important ecosystem services provided by coastal wetlands. We do hope that there's an increased availability of nutrients, as well as a balance of the nutrient ratios once that Phragmites has been managed. Reduced water evaporation, which potentially exacerbates the spread of Phragmites, and potentially reduced emissions of methane and other greenhouse gases. So challenges and opportunities. In putting this together, for every challenge, there really has been an opportunity. This project has been a tremendous learning opportunity and a really great partnership opportunity for the Canadian Wildlife Service. the major challenge, of course, is that we didn't have the ability to implement a best management practice. And so through a lot of effort, we were able to get approval to use the herbicide Roundup or glyphosate. And as of last year, there is now a registered herbicide for use in wetland areas. It's a different herbicide, but it is still very effective at managing Phragmites. There are a lot of optics associated with the use of an herbicide in a wetland area, applying herbicide from a helicopter, applying herbicide in the presence of species at risk. And so we've had to devote a lot of time to evaluate. It's easy to make assumptions, but there's really not a lot of research on the use of herbicides near species at risk. And so we're really happy to have been able to contribute to the research on species at risk, as well as just on the use of the herbicide. These sites that we're looking at, there are no roads to get there. This is 35 to 40 kilometers out into Lake Erie. It is a very remote site, very hard to access. And we've been very fortunate to have contractors and research partners that are willing to devote days of travel. And of course, our amazing team at their Protected Areas Unit who are willing to transport them out to these sites. There are very few contractors. This is the first time this project has been done. So how can you find contractors to do this work? Well, there are really just a couple of them. And so I know that over the next couple of years, I expect that they'll be a lot busier. So I appreciate that we got in on the ground floor with a few of these folks. One thing I want to mention was mentioned earlier was imperfect data quality. We are trying to look at very high resolution imagery because we're telling contractors where to apply herbicide. And so the margin of error that we accept is very small. And so the scale of aerial imagery, of satellite imagery has been quite a challenge for us. And so that's something that we've really been trying to rectify by working on a model with our science and technology branch, by collecting data in different ways. We're now doing some additional drone imagery this year, as well as doing a lot of ground truthing to try to get our data as accurate as possible, while recognizing that what appears in the field the day that you're doing management is not exactly what you may have predicted. And so just being flexible and understanding that what it looks like in a model or in a map doesn't accurately reflect what you might have on the ground. So having that awareness and appreciation. And the other challenge has been that there's a lot of people and a lot of partners working in this area. And that initially started, within CWS itself, with different units working on frag management or wetland management at Long Point, and then expanded to different branches and different areas of Environment Canada. And I'm still learning that there's all these folks doing work within this area, and I really do hope that this is an opportunity for us to continue to work together, knowing how important this area is, knowing how much Phragmites is a threat, knowing how successful we can be when we do manage Phragmites. So, this area, Long Point, is just really very special. And so on behalf of all of the partners involved in the project, we're proud to see this dial moving forward on the recovery of wetlands post-Phragmites management, as well as increasing the body of research in this area. And we look forward to working with others as we all continue to move forward on this. So thank you. I know I've gone over a little bit, but I'm happy to answer any questions.
Thank you so much for the great presentation, Heather. We are running a bit late, so in the interest of time, I hope it's okay if we save questions to the panel discussion at the end. And I will now invite our last speaker, Karen, to join us. Karen, please feel free to go ahead and share your screen while I provide a brief introduction. Karen Alexander is the policy coordinator for the Invasive Species Center and has over 10 years of experience working on Phragmites control programs in the Great Lakes Basin. And Karen coordinates Phragmites related projects, including the Green Shovels Collaborative and the ISC's work to advance novel collaborative financing tools that can support large scale control and management programs in Ontario. Karen, I see that your slides are up and in full presentation mode, so you're good to go.
Thank you, Sharon, and hello, everyone. I will be here to talk about novel approaches to collaborative frag management and finance. I'll first just quickly acknowledge that the Invasive Species Center is located in Sault Ste. Marie, the traditional territory of the Anishinaabe people in the Robins Treaty Area. And if you're not aware of the Invasive Species Center, we are a nonprofit organization and do work to connect stakeholders, knowledge, and technology. And our main interest is to prevent the introduction and spread of invasive species that harm Canada's economy, environment, and society. And obviously, one of these species we've heard a lot about today is Phragmites australis. And this one is causing significant harm to our economy, environment, and society. And it is a monster grass that's been really well described by some of our previous speakers. So I won't repeat anything about how aggressive this plant can be. But I will just mention this slide because I think we all consider frag to be an aquatic invasive plant and a significant problem in our coastal wetlands. But it is a plant that can tolerate a wide range of habitat types. And we know that it is using road allowances and other corridors like hydro lines and railways to rapidly spread across the province. So if we continue to do, or if we do nothing about this spread, it has the potential to continue to dominate in our coastal wetlands across the landscape in Ontario, but also head west to other Canadian provinces. And this is a very much of a concern to the Invasive Species Center. And we are working on 2 programs to reduce the spread and amplify control and management activities. So we're coordinating and participating in the Green Shovels Collaborative, and we're currently working with partners to investigate the potential role of conservation finance that would potentially have scale to address the invasive frag problem in the region in Ontario. So today I'm going to talk about each of these programs, and starting with the Green Shovels Collaborative. And this is a group of 6 conservation organizations that came together a couple of years ago with the common concern that invasive species are having a negative impact. With support from the Ontario Ministry of Northern Development, Natural Resources, Mines, and Forestry, the collaborative has been working in these 2 project areas. If you're interested in this innovative tools space, tools and techniques that meet the needs of land managers, I'll point you to our website. There's a lot of work there, but I don't have time to talk about it, so I'm going to focus on the Phragmites framework, which is where we're working together to develop an efficient and coordinated approach to prevent and manage frag in Ontario. So to guide that strategic framework vision to kind of bring this infestation under control, we first created these 4 objectives. And we've made significant progress under each of these objectives, and I'm pleased to share some of our updates with you today. So the first thing we set out to do was gather information and understand the current state of frag management in Ontario. And this was very important because as we heard in some of the previous work in Long Point today, frag control is not new in this province. There are actually hundreds of fraggers on the ground. And I say fraggers, and I'm referring to people who work on Phragmites. So fraggers in Ontario working really hard on control projects all over the province. And many of them are already sharing knowledge and resources under this umbrella group known as the Ontario Frag Working Group. These control programs are really not for the faint of heart. They're well organized, They're often volunteer driven and motivated by communities' interest in managing Phragmites and removing the impacts it's having. So this strategic framework we set out to create was really meant to build on these experiences and knowledge. So we used a survey, we did some case studies to look very closely at several of these programs, and we hosted a workshop to gather all that information on needs, priorities, challenges, barriers, as well as costs and control methods that are being used out there. And we took all that information and created these two documents, a cost benefit analysis and a strategic framework. And I'm going to talk about both of those, but I first want to say that while we were doing that work, we really didn't want to slow down the on-the-ground action. So we were able to create the Invasive Phragmites Control Fund. And we did that to distribute support out to these community groups working hard on the ground. To date, we've supported 30 projects and distributed $100,000. And we do hope that this fund continues to support Ontario fraggers in 2022. So on that cost benefit analysis, this was also a very important step to take because we wanted to ask ourselves the question, what is this going to cost? And what are we going to gain if we achieve what we set out to do? Another way to ask the question is, if we don't do anything, what are we going to lose? And this kind of information can be incredibly important if we want to build a case for significant investment that we know is going to be required to fight frag. So to start, you first need to kind of know generally how much frag you have. So we did that by using existing mapping information from the USGS and Ontario MPO. We estimated approximately 16,479 hectares of Phragmites infesting coastal wetlands and the road network. And then we applied some control methods that would be appropriate in those situations, and we reached a estimate cost of $90 to $109 million to control all of the frag in Ontario. On the benefit side of the equation, we know that Phragmites impacts many sectors, such as agriculture, tourism and rec, and so on, all the way down to property values. So we worked with the University of Guelph to compile existing data and made very conservative estimates for the benefits of controlling Phragmites. And we have to remember the economic benefit is always measured by the sum of the avoided costs of damages. So since we're talking about coastal wetlands in Ontario, let's look at that wetlands category and say we know Phragmites is causing impacts like flood control impacts, water supply, nutrient cycling. So the idea is if you remove Phragmites, you gain those services back. And we put a value on that at $12.5 million a year. So following similar logic in each of these categories, we quickly reach a potential benefit, per year benefit of $113 million. And then we also found this one-time benefit in property values that we estimate at $357 million when you remove frag from coastal properties. There's a big number to potentially gain. So this was the first time anyone tried to put numbers like this to frag control and benefits in Ontario. And the results, as conservative as they might be, provide good justification for significant investment in Phragmites control. And as we can see on the invasion curve here, we can see economic returns actually continue to increase as the infestation is brought under control. Which might seem like a daunting task to imagine bringing Phragmites under control in the province, but we do have now for the first time a draft framework that can help us get the job done. And this is a document that was created at a province-wide scale and has a number of recommendations under these 5 goals. And it really meant to support that coordinated province-wide response. So we are looking to, recommendations under how to better coordinate frag control, how to increase prevention control monitoring, ideas on program sustainability and creating access to multi-year financing. That's a big one because a lot of these community groups out there having success struggle to continue to fund their programs on an annual basis. So one option we're exploring is conservation finance, which I'll talk more about in a minute. And then there's other recommendations under policy and regulatory enhancement to ensure permits and advice are received at the right times of year, and then other ideas to ensure Ontario continues to be an innovative leader. This is a document that's available on our website, and it's free for anyone to take a look. So with that strategic framework and cost benefit analysis complete, we're now working on regional guidebooks to help Ontario fraggers transition their successful control programs from a site level to a community or municipal level, trying to inspire more regional collaboration. We know collaboration works. Let's try to get more of it going out there in Ontario. And we're also working on engagement planning for Indigenous communities. We'd like to incorporate more traditional knowledge into the work we've done so far and work going forward. And we've got some investments into some communication strategy to increase public awareness. And you may have seen some of these headlines in your local papers in recent months. So the Green Shovels Collaborative has been at this for a couple of years now. And we have, with thanks to the generous support of the Ontario government, laid out a path to see Ontario frag free by 2033. We know what to do, we know how to do it, and we generally know what it might cost to get the job done. And the fact is, it's not going to be cheap. So we're also working with partners to explore ways to potentially finance this undertaking. And one of the things we're looking at is conservation finance, which is starting to gain a bit of traction in Ontario and Canada, and does provide opportunities for public and private partners to share the cost of expensive programs. And really, it's about building on that cost benefit analysis. We're confident that the frag control, the cost of control, is going to be less than the benefits that we will gain. But there currently doesn't exist any kind of financing or funding framework to capitalize on these benefits. We have this wide range of beneficiaries on the landscape, and they're all gaining from the investments in frag control, but we don't have a way to take that benefit across all these sectors and turn it into real dollars that support on the ground work. So we think conservation finance is a potential way to leverage and coordinate these multiple beneficiaries and ensure the financial burden doesn't fall on one entity alone. We're really just getting started in this space, and we do hope the project can demonstrate an economically feasible approach. We've done 4 webinars to date and had really positive feedback, and we're now looking to create a conservation finance group to facilitate more conversations about this opportunity and essentially address the Great Lakes, or frag in the Great Lakes. So if anything I spoke about resonates with you today, please get a hold of us at info@greenshovels.ca. And I like to just say we're really only looking for people who are as enthusiastic as this young man. But of course, we'd love to hear from you either way. And I'll just thank you to the Environment Climate Change Canada for having us today and all our partners. And I like to leave off with this picture of a restored coastal wetland post Phragmites control on the Lake Huron shore, because it's nice to take a look at what we've lost and where we can go.
Thank you for the great presentation, Karen. In the interest of time, I would now like to invite all of our speakers to join us for our final panel discussion. Great. Thanks for joining us, everyone. So we know that we covered a lot of ground through this webinar session. So we'll try to touch on the different themes that we covered, starting with invasive species management, especially with Heather Braun and Karen, because we didn't get a chance to ask you questions after your presentations. How do you think the modeling results that Marianne and Dominic presented will be helpful for the ongoing management of Phragmites across the Great Lakes? Starting perhaps with Heather Braun.
So I'm thinking, selfishly about the areas in which that information aligns with where our national wildlife areas are. And so on Lake Erie, as well as a couple areas on Lake St. Clair. And we have a national wildlife area on Lake St. Clair where we are looking to expand Phragmites management as early as this fall. And so I think your monitoring results support our plan to initiate that management at St. Clair. I do think that from a regulatory perspective. We have at St. Clair some managed wetlands with berms around them and water control structures. And on federal land, from a regulatory perspective with the Species at Risk Act and federal agencies that manage that, it has been a bit of a challenge to do any sort of drawdowns or the typical wetland management that would normally take place in wetlands that are managed. So I'd be curious to see at the end of the day how those models and that information may also help inform some sort of regulatory decision making.
That's great to hear. Thanks, Heather. And Karen, do you care to also give us a brief reaction to the modeling results presented by Marianne and Dominic?
Yeah, sure. I think they're really inspiring to see that from my perspective, where I would like to maybe take some of that information. The ISC tends to focus on catalyzing action, sharing knowledge, and then building that case for investment in our ecosystems and in our environment. And I think some of that information, if we can kind of make it public friendly, could really help inspire some of the work that we're doing, kind of coordinate and see the growth of interest in frag management in the province.
That's great. Thanks, Karen. And inviting Joe and Heather Pankhurst to see if either of you have any reactions to the modeling results and how you might want to use those results in your work.
Yeah, nothing too specific to add. Just say that the model, our group focuses largely on the monitoring side of things, but the modeling piece is not too far removed from that. It informs a lot of what we do, and a lot of the work we do also feeds back into the modeling. So it kind of comes full circle.
Great. Thanks, Heather Pankhurst and Joe. And staying with Heather Braun and Karen for a little bit more, for community members or citizen scientists interested in getting involved in invasive species management, what would you suggest? Perhaps starting with Karen?
Sure, absolutely. While there's multiple ways to get involved in invasive species control in general, we work on more than just Phragmites at the ISC. So certainly reach out, and I could point you in the direction of multiple programs. In terms of community engagement on Phragmites, I think what the Green Shovels Collaborative is ultimately trying to do is inspire more regional collaboration and more partnerships on the landscape to see a broader kind of perspective on how we're tackling Phragmites. So it would be, one great way to get involved is to contact us and find out if there's either a collaborative started in your area or maybe a working group already that exists that you may be able to join.
That's great. Thanks, Karen. Heather Braun, did you have anything you'd like to add?
I don't really have anything additional to add. I would like to point out that there's a large suite of resources available to inform potentially participants who are newer to Phragmites management and understanding the long-term nature and ins and outs of choosing your approach that are available on greatlakesphragmites.net, which is the Great Lakes Phragmites Collaborative's website. So lots of good information, background, case studies, as well as a lot of webinars.
Great. And staying on invasive species management for a little bit longer, open to Karen, Heather Braun, Heather Pankhurst, or Joe, in terms of whether there are any invasive species on your radar that you think might pose as key challengers to coastal wetlands under a changing climate. Apart from Phragmites, as we were already seeing, I see Marianne wants to jump in, so perhaps we'll have Marianne go first.
I want to take note because maybe we can model that species. But I was thinking about zebra mussel. So since you're more an expert of invasive species, regarding climate change, I'm thinking that species may expand, especially with all the wreck boating on the Great Lake. So I was thinking that maybe in another phase or another project, it may be a species that may interest people like Heather Braun. It can be another species.
No, there's definitely a big blanket of zebra mussels and quagga mussels in Lake Erie, and a lot of trials in the US on ways to to deal with that. And I would also say, Asian carp, from an aquatic species perspective, it's not moved up to this area in the Great Lakes yet, but it is on the radar of a lot of folks. From a plant perspective, there are a variety of species. European frogbit is certainly present, but it doesn't seem to have the same impacts that Phragmites does. There are all sorts of other species as well. Butemus, species that are here and that are hanging out, sort of waiting. And we're fortunate that we haven't seen a major resurgence, secondary invasion. But there are, hybrid cattail is always going to be a little bit of a bane. Japanese knotweed, those sorts of things. So I still think Phragmites is the big villain here. But looking forward to what comes next, I guess.
Thanks, Heather. Karen, did you want to go next?
I think Heather hit most of them. The one I might add is European water chestnut. That one is not quite yet established in Ontario and Canada, and it's coming potentially. There's a few control programs going on, but it has not established anywhere near what Frag has been able to do. And I think that's one we want to watch and respond to quickly. We wouldn't want it to reach the same level of establishment.
That's great. Thanks, Karen. And I think that touches on a participant's question about the impacts of delayed action and why early action and detection is really important. Heather and Joe, anything you'd like to add to the list? Heather Pankhurst, sorry.
Throw in starry stonewort is another big one, really common, become increasingly common over the last number of years. Certainly well established in Lake Ontario at this point, but something to keep an eye on.
I guess I'll just add another perspective. I think a lot of these invasive plant species are, like Joe said, well established, and in a lot of our degraded wetlands, they're the predominant species. If we were to remove all Phragmites, all hybrid cattail, all of these other plants, in a lot of these wetlands, we wouldn't have much left. So I think going forward, we really have to think about some of these plants as, endemic, and that how are we going to, just adapt to them being here. So.
That's very helpful. Thanks, Heather and everyone. Now I'd like to shift our focus a little bit to coping with extreme water levels and address this question particularly to Mike and Adam. But if, again, any other speakers would like to chime in, please just give me a signal. So Mike and Adam, for communities worried about more extreme high and extreme low water levels due to climate change, do you have any words of advice to share with them on how to prepare for or cope with more extreme water levels? Perhaps we'll start with Mike.
Yeah, thanks. I guess, yeah, so in our work, we're not as much on the sort of adaptation side, so the coping side for the work we've done with our adaptive management committee, but certainly recognize that, to expect sort of variability in water levels into the future and sort of from a planning perspective, I guess, to prepare for not just what we've seen historically, but prepare for conditions that might be beyond what we've seen. And even if you're, as you're planning for future, whether it be, shoreline adaptation or, ecosystem sort of restoration or, other developments along the shoreline, just kind of making sure you're preparing for, beyond what we've seen in the past as sort of a framework for going forward into the future.
Thanks, Mike. Adam?
Yeah, I guess some of the things that I think of when I work with communities is certainly identifying those highest priorities, because you can't protect everything or tackle every project. So what are the most critical assets to function, whether they're natural assets or infrastructure assets, and then making sure that those sorts of things get built into long-term planning mechanisms, because it's so easy to forget about the high water levels and have staff turnover and then be worried about low water levels when they come and then forget about high water levels. So I think definitely you noticed that in this recent high water level stand of a lot of staff and property owners dealing with this for the first time and sort of not being prepared for these extremes we see. So making sure we kind of act now to use those institutional mechanisms.
That's great. That's very helpful, Adam. And Mike, we had an earlier audience question about the limits of water level management or regulation. Can you speak to what some of those limitations are and what you expect we might continue to see moving forward?
Sure. I think some of this ties back to the presentations that Frank Sigleniaks made on the first day of this series. I think there's not much in the way of sort of mechanisms to control water levels on the Great Lakes. There's the outflows from Lake Ontario, and to a much smaller extent, some influence on the outflows of Lake Superior. So really, I think in the long term, we, as part of our processes to look at those structures and how they operate, we will be building in the newer climate change science and considering how how that might push the system even more into the future. But I think sort of the bottom line is kind of referring back to what I said before, is that we can expect the changes in water supply are what drive water level changes on the Great Lakes. And if those change in the future under climate change, then we have to be able to respond to that in different ways. And I don't necessarily see the current systems that we have in place are not going to eliminate water level fluctuations in the future. There's just not that capacity in the system, right? So we have to be thinking about how we respond in other ways along the shoreline, in terms of how we manage the system to be more adaptable or more resilient, I guess you could say, to the changes that might be coming.
That's great. Thanks, Mike. And Adam, just to touch on our other theme about managing diked coastal wetlands, I wonder if you came across any diked coastal wetlands in your research, and especially through your case studies, and what nature-based options are available for diked coastal wetlands?
So I didn't really come across them. We don't have a whole lot of them in sort of that study area in Wisconsin that we were sort of radiating out from. So I didn't have much focus on that, but I think when it comes to ensuring that the connection with the lake is stable and things like that, I think obviously building in some of these nature-based elements could be a critical opportunity, and especially in some of the lower wave energy areas, thinking maybe not about a diked coastal wetland, but some park lagoons in Chicago area that are facing impacts from high water levels. They certainly don't see the wave energy of the open coast, but could use some natural shore protection as opposed to just rocking everything. So.
Thanks, Adam. And Greg, if you are with us, we do have a question about focus on or applicability of the adaptation strategies to the upper Great Lakes, recognizing that the vulnerability assessment focused mainly on the lower Great Lakes, and whether the adaptation strategies we've been presenting yesterday, today, and tomorrow are applicable to the upper Great Lakes, like Lake Superior as well.
Yeah, thanks for that question, Sharon. It is a good question. And in the development of the white paper on wetland resilience, we recognized a real challenge in finding case studies and applying them to the shield areas. But when you think about what we've talked about so far, water quality, that should be a resonating theme for everyone. Wetland water quality needs to be maintained and in many cases improved. And where it is in good shape, it needs to be definitely maintained and protected. So that is applicable to all of the Great Lakes. Connectivity with the aquatic ecosystem as well as the terrestrial system. There are places even in the upper Great Lakes that are facing greater development. So we need to protect and make sure that those wetlands can transition waterward and landward and maintain the connectivity. Let's see now. I mean, there's many that obviously Phragmites, as we talked about today, it's a growing concern also for the upper Great Lakes. And Karen has done a nice job of demonstrating that in her map of the distribution of Phragmites. That is definitely applicable to the upper Great Lakes. And in the white paper, we did encourage the thinking around collaboratives on a regional basis. that's imperative. It's so costly. It's so overwhelming to try and manage Phragmites independently of a larger body of or network of individuals. That's actually occurring in Eastern Georgian Bay with Georgian Bay Forever and some of their partners. But the approach needs to be encouraged elsewhere, and we're seeing some really positive trends. So in general, yeah, there's many adaptation options that are applicable to the shield area. Obviously, diked wetlands are something that have been around for 60 or 70 years in the southern or the lower Great Lakes, and not so much in the northern areas. So yeah, you know what, it's fodder for future discussion. It's an entryway into future discussion as well. And I think we need to build on this work and integrate more case examples and make them available to people so they themselves can learn from them. Thanks.
That's great. Thanks, Greg. And a question from the audience is whether there are programs or actions that you're aware of currently to stem the spread of invasive species further north as the climate continues to warm, or any of you, particularly perhaps Greg, Heather, Braun, and Karen, that you're aware of focusing on invasive species management in the north?
I mentioned one. Eastern Georgian Bay Forever, Georgian Bay Association, the Eastern Georgian Bay Biosphere Reserve, the Stewardship Council. I think they're all working together in Eastern Georgian Bay to work with the stakeholders and just limit that spread and control and eradicate Phragmites where they do occur.
Great,
Yeah,
thanks, Greg.
I was gonna add the same things, Greg, and I do know that there are variety of projects that have been funded by Environment Canada in northern areas for invasive species. But I think Karen might have more to add on this as well, given her position.
Absolutely. There's a lot of collaborative work going on Manitoulin Island.
Yeah.
There's a huge interest in the Green Shovels Collaborative as and the core groups to move the programs and our resources north to stop the spread. Like, it's really about kind of beating it back south, right? Like, don't let it get established in the north the way that it has in Southwest Ontario. So that, you know, that idea of encouraging more collaborative knowledge transfer and working together is one we'd like to see as well continue.
Yeah, and I might add the Nature Conservancy of Canada also works with local stakeholders on Manitoulin Island. They work with Manitoulin Streams, which has been focused on fisheries and mostly aquatic habitat restoration within streams, but they are very concerned about the Phragmites on Manitoulin. The Nature Conservancy of Canada has acquired a lot of lands on Manitoulin, and they all need to be managed. So I think it's a growing concern, and it's a groundswell of activity out there.
That's great. And if we can just end with a lightning round so that everyone can have a chance to say one more last word, is what is a recent development that is giving you most hope or cause for celebration in your area of work? Anything, any new good news item that you would like to share with us? Perhaps starting with Greg?
Sure, that's a great question. I find the evolution of thinking around resilience and adaptation really fascinating. We started this 4 years ago when we had no understanding of what vulnerability is, how to operationalize it, least of all. Resilience remained a very nebulous, vague, esoteric and theoretical thought with not a lot of application. Every time I go onto the website and I do a quick search for resilience and adaptation, I see more and more fascinating papers from North America and Europe and elsewhere. Not as much in the Great Lakes Basin, but I even see that that's changing. So I think it's a really quickly evolving study, and that provides me with a lot of hope.
Thanks, Greg. And moving next to Mike.
Yeah, I guess I would just briefly say that, you know, even just participating in these sessions over the past couple of days, just the amount of interest and collaboration on these different themes that are connected, overlap. You know, the brain power and capacity that's out there is really exciting to see how these things can continue to push us forward in the future to improve things going forward.
Thanks, Mike. Joe, how about you?
I think maybe one of the most encouraging things is just the attention that coastal wetlands have received over the last little while. I think historically they've been considered a marginalized ecosystem and not thought of all that much. But we're having events like this now. We're taking a whole week talking about coastal wetlands, and there's all these great large-scale programs and all this work that's being done all over the basin. So I think, hard not to be encouraged when there's all this great work going on.
Great, and I'll save the last word for Adam, so I'll go to Heather Pankhurst next.
Yeah, I'll say one of the most encouraging things is really looking at coastal wetlands in a watershed context and not in isolation, and looking at how we can improve our watersheds and the impacts there, and how that really ties into coastal wetlands and connectivity as well.
Thanks, Heather. Marianne.
I have something different. So for me, the GLIPI project is one of the first projects I work on, not in silo. And for an institution like Environment Canada, most of us, not all of us, but some of this panel are from Environment Canada. It's not easy. We have a large country. We have 2 languages. We have different watershed, water bodies. And this project for me is really successful because we were able to work with different teams, but also really for real with multidisciplinary profile, not just in my team, but in other team too. And we were able to work together. So that's a big accomplishment of that project.
That's great. Thanks, Marianne. And Dominic.
Yes, well, for me, the wetlands are fairly new in my career. Like it's been like maybe 2 years since I'm in this project, and at the beginning of my career in Environment Canada. And what I really enjoyed in this project is that I see that all the collaboration from with the Canadian Wildlife Service and all the different agencies we use to monitor the phragmites, build the models, and also I like to see. We predict where the phragmites may be, and it's also great to see how they eradicate it and how they restore wetlands and everything. So this webinar has been very cool to see all this information gathering for me.
Great, thanks, Dominic. We'll go to Heather Braun, Karen Alexander, and then Adam.
So 2 things, just on a very practical level. It's exciting in Ontario to see things like the recent approval of an aquatic herbicide, which I hope will be helpful and will be used wisely. I also am encouraged by recent advancements in things like biocontrol for invasive Phragmites. And so I look forward to that, as well as other biocontrol type activities moving forward. But I think for the most part, for years, there's been a divide between land managers and researchers and planners. And through this connection to coastal wetlands, it's really an opportunity to bring us all together so that managers can learn from researchers and research can inform management, and doing that sort of exchange where there's been a bit of a divide historically. So I look forward to opportunities to working with all the folks involved in this webinar in the future.
I guess from my perspective, I'm most encouraged by things, I guess the response, the investment in prevention, and what I'm seeing, I suppose, is more awareness in the communities in the north, and just more people becoming a little bit more tuned in to the threats that might affect them and their ability to, say, enjoy coastal wetlands and the ecosystems that the Great Lakes offer. And I think we're seeing more of that at the Invasive Species Center with inquiries from various communities around the province and in the north asking, what do we do? How do we stop this? How do we get on this right away? And I think that gives me a bit of hope that the message is getting out there, and doing these types of webinars and bringing all of this information together for the public, it is just kind of helping me see we're moving in the right direction.
That's great. Thanks, Karen. And our last word to our friend from the States, Adam.
Yeah, I guess build on what Karen was saying, but maybe for my specialty, which is the, coastal engineering and resilience, is that sort of demand and awareness for resilience. Getting questions, frankly, that I can't answer, like what should we design to? What are the sort of anticipated conditions in climate change, or recognition of the impacts of increasingly hardened shorelines and how we can maybe do things better? So I think there's a lot of energy out there moving in that direction, and that's really energizing for me.
Wonderful. And that officially brings us to the end of our panel discussion. I'd like to say another big thank you to all of our speakers for your excellent presentations today, and for your ongoing work, and for staying with us to the very end. I know we did go over time, so thank you again for your patience and understanding. I would also like to thank our project team, Greg, Anders, and Patrick from ECCC, and Megan, Jessica, and Krista from TRCA for making this webinar possible. For questions that we were not able to cover within our time today, we will follow up with speakers for some brief written responses, which we will share along with the presentation slides and recording. And we anticipate that the slides and recording will be available in a couple of weeks following the webinar series. Our final webinar is tomorrow, where we will continue our focus on possible adaptation strategies and options for enhancing coastal wetland resilience. And tomorrow's session will focus on identifying climate refugia and advancing wetland conservation and protection. And we have another exciting lineup of speakers tomorrow, including Scott Parker from Parks Canada, who will be speaking with us about coastal wetlands in a protected areas context, Robin Rumney and Dan Kraus from the Wildlife Conservation Society. We'll speak about identifying key biodiversity areas to support Great Lakes coastal wetland conservation. And finally, we will hear from Kristen Bernard on the Nature Conservancy of Canada's Great Lakes conservation. And what a great way to end the series. So we hope you'll join us tomorrow. And now I would like to call on Greg to say a few last words and share some upcoming reports and resources.
Thanks, Sharon. I'm not going to take very much time, and I've said this repeatedly over the last few days, but I just want to draw attention to the invasive species modeling today. That will be contained within a large technical report on the coastal wetlands response model. That's number 2 on this slide. All reports, of course, will be completed and made available to the public, including the report that we spoke of today, Adapting to Climate Change Solutions to Enhance Great Lakes Coastal Wetlands. We're also working on a highlights report, which summarizes all of the technical work and puts it into a public-friendly version, and that will also be made available. That's seven technical and public-friendly reports in total. I hope that people are enjoying the webinar, but also will refer to these technical and public-friendly documents in the future. Thank you for joining, and thank you to our speakers. You guys are amazing. You really brought to life many of the concepts that I tried to convey in the solutions to enhance Great Lakes coastal wetlands. So thank you very much.
That's wonderful. Thank you for those closing remarks, Greg. Thank you everyone for joining us, and take care.